First, I will discuss major ideas which we discussed after. Okay, discussed, which we talked about after the second midterm exam, right? And then I will start solving problems over here, right? And sort of this is will be my reference board. And of course, this whiteboard will be photo of this whiteboard will be attached to the notes, to my notes of the exam review session. Right? Okay, so we started, after the second midterm exam, we started discussing magnetism, right? And first we introduced all major equations, fundamental laws, which we need to describe magnetic field production, right? And so if you have a piece of wire with a current, right? So, of course, this current, because there are moving charges, and if there is a moving charge, there will be a magnetic field around that charge. And since we have here a bunch of moving charges moving in the same direction, of course, there will be a magnetic field around that wire. So how can that be found? There is a fundamental law which based on observations. So at a distance r from the wire, so you need to take an infinitesimally small section of the wire ds. Direction of that ds is determined by the direction of the current, and then Biot-Savart law. Magnetic field at that point, it's a mu naught nu universal constant divided by 4 pi, then the value of the current and the cross product between ds and r hat. R hat, it's a unit vector which shows the direction to the point where you want to find the magnetic field, right? And divided by the square of the distance between them, right? So we applied that, and then we applied this formula for an infinitely long straight wire with the current, right? Current I. And in this case, we found that the magnetic field created by this wire can be found using this formula, mu naught times I divided by 2 pi r, where this r, it's the shortest or perpendicular distance between the wire and the point in question, point where you want to find your magnetic field, right? All right, so that's the magnitude of the magnetic field. And then if you want to find the direction, you just need to remember that magnetic field lines form circles around the magnetic field, around the wire, circles centered on the wire. And then how can you find direction of those magnetic field lines? Right hand rule number 2, outstretch your thumb in the direction of the current and curl your fingers. I'm thinking, do I have some long piece of... I can use marker. Sorry, I can use marker. I have tons of markers, right? So if this is piece of wire, right? So outstretch your thumb in the direction of the current, and your curl fingers gives you direction of the magnetic field lines. So that is the correct direction for this situation. So then, after that, we introduce an alternative way of finding magnetic field using Ampere's law, right? So you pick any closed loop, you can call it Amperean loop, right? And calculate that integral b dot ds, and that must be equal to mu naught times the total current within your chosen Amperean loop, right? Then after that, so this Biot-Savart law and Ampere's law, that's what can be used to find magnetic field. And after that, we moved on to introduce the next fundamental equation, because now you need to know how these magnetic fields interact with material, with charges or currents, right? So we introduce magnetic force. First, magnetic force on a charge, and the charge must move. Everything, you remember I told you, in magnetism, everything is in dynamics. In order to produce magnetic field, charge must fly, right? Charge must fly. If a charge wants to experience magnetic force acting on the charge, right, then of course charge must fly over here. So if there is a charge and moves with velocity v, and if that charge is exposed to the magnetic field b, then the force can be found F equals q and the cross product of v and b, right? Okay, guys, can I ask you quickly, there must not be any delay between my voice and the video, right? If there is something like this, tell me, right? But so far it should be okay. I just started thinking and worrying, right? If there is a delay, just tell me. Okay, then if there is a wire with a current I exposed to the magnetic field, and let's say length L of the wire is exposed to the magnetic field, then we can find force acting on that piece of wire of length L using this. F equals I L cross B. Direction of L is determined by the direction of the current. Again, we use this formula practice, so it shouldn't be new for you. So those are magnetic forces. And after that, we started discussing Faraday's law, because that was something new, and we realized that that phenomena which Faraday observed couldn't be explained by what we introduced before, right? So we introduced the new law, Faraday's law, which is if you have a loop, conducting loop, exposed to some external magnetic field, and of course if there is a magnetic field, there must be magnetic flux through the loop. And if that flux through the loop changes in time, then there will be EMF induced in the loop. And of course, there will be induced current flowing either in the clockwise direction or counterclockwise direction, right? Okay, so, and that EMF can be found using this Faraday's law. EMF equals minus rate of change of the magnetic flux through the loop, right? Then, and of course, magnetic flux can be found as a dot product between magnetic field and the area vector. Then, all right, so in order to describe that minus, we introduce Lenz's rule, right? Instead of using that minus, we can use Lenz's rule in order to find the correct direction of the induced current. And let me mention quickly, if magnetic flux through the loop is constant, then loop doesn't do anything. The loop doesn't like when flux changes in time. If the flux is constant, a loop basically will be sleeping, right, without doing anything. But once flux starts changing, if, for example, flux is dying in time, then of course loop will start doing something. It will start driving current, induced current, in such a direction so that the induced magnetic field within the loop will be in the same direction as the external magnetic field. As I told you, in this case, loop becomes supportive, behaves like Florence Nightingale, right, supporting dying flux because it wants to keep flux as constant as possible, right? And then once you know direction of the induced magnetic field, you apply right-hand rule in order to find the correct direction, right, in the loop. Second situation, if magnetic flux is growing through the loop, again, the loop is not going to like it. And in this case, it will try to suppress it. It becomes like a rebel, like Che Guevara, I compare it, right? And in this case, if flux is increasing, then induced magnetic field within the loop will be in the opposite direction to the direction of the external magnetic field. And now, once you know direction of the induced magnetic field, you can apply again right-hand rule number 2, in order to find the correct direction of the induced current, clockwise or counterclockwise, right? Okay, so we'll practice that. Okay, after that, after we introduced Faraday's law, we realized that at that point we could explain the work of an inductor, of a solenoid, right? And basically because behind the work of an inductor, just Faraday's law lies, right? It's all Faraday's law. And so first we introduce the inductance, right, as the total flux through the inductor divided by the current which produced that flux. Right. Then we applied that formula for a solenoid, right, just a regular solenoid, and we found that it is equal to our new universal constant mu naught, square of the loops, square of the number of the loops, right, and times cross-sectional area and divided by the length of the loop, right? So that was application of this formula for a solenoid, right? In the solenoid, you remember, it's a device which allows us to create a uniform magnetic field inside. Inside of a solenoid, there's a uniform magnetic field. Then we apply Faraday's law for a solenoid in order to find potential difference across a solenoid, right? And we found the delta V. So if this is solenoid, right, and there's a current flowing through the solenoid, and potential difference, what is this? What does this potential difference mean? It's a potential difference between the final point. Since current exits solenoid at that point, so that's the final point. Since current enters the solenoid at this point, so that's the initial point. So delta V, it's a V final minus V initial. So that's delta V. So we found that delta V equals minus L and rate of change of the current. So in this case, delta V is produced only when current changes in time. We will look at the example, and for this situation, we sort of adjusted this Lenz's rule in a slightly different way. Let me just quickly say in words, and then when we get to the example, I will write everything, right, and draw everything. But now briefly. So pretty much in this situation, when you apply Lenz's rule for this more complicated system, because what is solenoid? It's just a bunch of identical loops stuck together, positioned together, right? So of course you can apply the same Lenz's rule, but now it's better to adjust it and present it in a slightly different way. Which way? Now we can say that this inductor doesn't like when original current, this current, changes. So if this current is constant, of course, then the delta V will be 0. Nothing happens. But if this current starts increasing in time, inductor is not going to like it. It wants to keep current as constant as possible. So what will this solenoid do in this case? It will create the potential difference across itself so that induced current produced by the solenoid will flow in the opposite direction to the direction of the original current, suppressing it, trying to keep current as constant as possible, right? So now you see we're either supporting current or suppressing a current. And then second situation, if this current is dying in time, again, the inductor is not going to like it, and it will produce this potential difference across itself, delta V. Since original current is dying, so it wants to support dying current. It will start driving induced current in the same direction as the direction of the original current, right? So now you see we're supporting current or suppressing current. Over here, we were supporting flux or suppressing flux. So we basically slightly adjusted Lenz's rule for the case of an inductor. Okay, we'll practice that. So after that, we finalized Maxwell's equations. We wrote them down. We started playing with them, and naturally we started moving towards electromagnetic waves. But before we introduced electromagnetic waves, we digressed a little bit in order to introduce traveling wave equation. So whenever you have a wave, any wave, it can be described. It can be described using this equation. A sine kx plus minus omega t plus phi naught, right? So you remember we played enough with this equation, right? So where k is the wave number, it's basically spatial frequency, and we introduce it as 2 pi divided by spatial periodicity. Wavelength, it's a distance over which wave reproduces itself, spatial periodicity. Then it's this k, wave number. Then omega, angular frequency, is introduced in exactly the same way, but now 2 pi divided by temporal periodicity. Here 2 pi divided by spatial periodicity, here temporal periodicity, right? And how can we find speed of this wave? It's either omega versus k or lambda times f. Again, we derived that, right? And then we applied these traveling wave equations for electromagnetic waves. All these ideas, because electromagnetic wave, one of the waves, and of course it's a transverse wave, right? So electromagnetic wave, in the electromagnetic wave, all the time, these 3 directions, direction of electric field oscillations, magnetic field oscillations, and direction of propagation of the wave are perpendicular to each other. It must be this way. All right, and amplitude of the electric field and amplitude of the magnetic field in the electromagnetic wave, they are connected to the speed of light. So numerically, electric field amplitude is way, 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 way larger, stronger than the magnetic field amplitude. Speed of light, it's a 10 orders of magnitude. It's a gigantic difference, right? Okay, so here I draw electromagnetic wave, which propagates in the x direction, you see. V in the x direction, this axis is y and this axis is z, right? And so in this case, I assume that the electric field oscillates in the y direction. You see it goes up, then down, up and down, right? So electric field traveling wave. And then on top of that, in the electromagnetic wave, there is a second traveling wave, magnetic field traveling wave, which oscillates in the perpendicular direction, in this case, z direction. Up, down, okay, left to right, and so on. And they oscillates in phase, in unison. It means what? It means that that this time and x dependence, this sine kx minus omega t plus phi naught, and here exactly the same for the electric field and the magnetic field. So this part, okay, this part is exactly the same for both waves. So difference only in the amplitude, right? and direction of their oscillations. Electric field oscillates in the y direction, so direction of oscillations are shown in this subscript. And magnetic field oscillates in the z direction. Right? Otherwise, x and time dependence exactly the same. Right? Okay, so then after that we started looking at the interference, basically superposition of two waves. For example, superposition of two electromagnetic waves, right? Or sound waves of any waves, right? So interference. Let's say we have two, in the case of the acoustic waves, let's say we have two speakers, speaker number one and speaker number two. Of course, both of the speakers generates their own waves, right? Okay, if we look at the cross section, we can say circular waves, right? Of course, spherical waves, but let's say circular waves, right? And you see, I drew a bunch of wave fronts. Wave fronts, collection of crests, and of course, at the center between wave fronts, there are troughs, right? And so let's say, and we assume that these two waves are identical, basically, right? So the same amplitude, the same wavelengths, and the same frequency, right? So in that situation, these two waves can interfere constructively and destructively. So let's say if we take a completely arbitrary point in space, and then we can ask ourselves the question: what happens at that point? Are these two waves interfere constructively or destructively? So in order to answer that question, we derived that you need to analyze this expression. You need to calculate phase difference, which is 2 pi over lambda times delta r. What is delta r? It's the path length difference. It's just additional length that, for example, the second, or in this case, the first wave has to cover in order to reach the point in question relative to the first wave, right? Path length difference. And then delta phi naught, it's a difference in their initial phases. It's basically phi 20 minus phi 10. And we gave it a cool name, the inherent phase difference. But it's just a difference in their initial phases, right? And if you calculate if that is equal to integer number of 2 pi's, it means that at that point we're going to observe constructive interference. M is an integer, 0, 1, 2, 3, and all the way to infinity. And then if that is equal to m plus 1, 2 times 2 pi, destructive interference. So for example, if here we have constructive interference, if you move slightly away from that point, then you will find destructive interference. Then again constructive, then destructive, constructive, destructive. So pretty much you can have infinite number of points with constructive and destructive interference. Right? So that's we discussed, and after that we move to the interference of electromagnetic waves, right? Light. Actually, interference of light. So we discussed double slit experiment and natural transition from double slit to a diffraction grating. So double slit, you have two narrow vertical slits, right? Distance between them is d. Distance to the screen is L. And then on that screen, you're going to observe what is called interference fringes. Collection of bright spots, dark spots, bright, dark, right? And so you can define their positions, those bright spots, using either the angle, theta, or, which is more convenient, distance from the center of the screen to the point of your bright spot, which you want to locate. So we derive the formula for this distance along the screen, which is equal position of the mth bright spot equals to integer m, again, 0, 1, 2, 3, and so on. And lambda times L divided by d. Again, L is the distance to the screen. Right? Then diffraction grating. Again, it's a natural transition from double slit to the diffraction grating in order to improve the quality of a device, which can be used in optical lab. So you reduce the distance between slits and increase their number to several thousand. It's not just 2 slits, but several thousand slits, very, very closely positioned. In that case, basically you create a diffraction grating. Again, you position the screen at the distance L, and then on that screen you are going to observe much brighter spots and which are spread over longer distances. So it's much more convenient to use in the lab. So at the center, again, all the time there is a bright spot, then a bright spot corresponding to m equals 1, m equals 1, then m equals 2, m equals 2, right? And so now, in order to find the positions of those bright spots, you have to use these two formulas. First allows you to find the angle to the bright spot, d sine theta m equals to m times lambda. And then, since measuring, since it's not very convenient to measure angles, these angles in the lab, so it's better to make a transition to the distance along the screen. And that transition can be made using this formula ym, this distance ym, equals to L times tangent of that angle which you found in the first equation, right? Again, we practice that. All right, so after that, we said enough of wave optics. Let's move into ray optics, right? And in ray optics, we use rays, basically straight lines, to discuss behavior of light, right? And in ray optics, we introduce two laws, right? Law of reflection and law of refraction. So if you have two medium, let's say we have up here medium with index of refraction n. And how did we introduce index of refraction? It's a speed of light in the vacuum divided by the speed of light in that particular medium, right? So that's how we introduce index of refraction. The smallest index of refraction is 1. So pretty much index of refraction all the time is larger or equal than 1. So let's assume that we have a medium with index of refraction n1 and then medium with index of refraction n1. Oh, n2, sorry, n2. So, and let's say send one of the rays. So then part of that ray will be reflected, and angle of incidence equals to the angle of refraction. First of all, we define directions of these rays using this angle, the angle between the normal line and the ray, right? So don't use that angle different, which complement that one to 90 degrees. Use between the normal line and the ray. So angle of incidence equals to the angle of refraction. And then Snell's law, which describes refraction. Basically, the process of transitioning of light from the first medium into the second one. So n1 times sine of theta 1, angle of incidence, equals to n2 times sine of theta 2. Theta 2, it's an angle of refraction. Again, angle between the normal line and the ray. So we've practiced that, and we will practice more. And after that, we discussed basically what yesterday and the day before yesterday, we discussed lenses, right? So lenses allows us to find images, allows us to create images, right? So, and of course, we needed to find positions of those images and characterize them, right? And we use two methods. First one, ray tracing. We will look at a couple of examples. And then the second, algebraic method, where you have to use these two simple formulas. Lens formula, which connects focal length and image distance and object distance. And then magnification, which is the minus ratio of image distance versus object distance, right? Okay, so pretty much that's the scope of the new material which we discussed after the second midterm exam. So at least, as I said, 60 or 70% of the exam will be based on this material, and then something from the past. But we're going to discuss only that. Okay, guys, make sense? And now, if you don't understand something, or something is not clear in terms of my handwriting, right? Just start saying that, and start talking, and of course I hear you, and I can respond, and I can react and explain something, explain deeper, or clarify if something is not clear, right? At any moment. So let me look. Okay, so number of students went up slightly. And so now let's start with magnetism. Right, let's start with magnetism. I'm not going to discuss application of this formula because it's significantly more complicated. We solved this problem using Biot-Savart law. We solved only one problem using Biot-Savart law in the recitation class. And so I want to use this formula. Let's start with that. So what do we have in this problem? Let me label it first. It's a number 1. we have two infinitely long straight wires with current. One wire current is what? Out of the board. The second one, no. The first one into the board, the second one is out of the board. Let me draw the situation. First, probably I draw horizontal line. Something like this, right? And now these two currents, wires with the currents. So the first one is over here, and that is cross. It means into the board. So it's a wire number 1 and current I1. I will write the value of those currents in a second. Then there's the second wire at the distance D. All right, so let's say this. And you see, dot. It means it's out of the board. So that's the wire number 2 and the value of the current I2. And as I said, distance between them is given D. Okay, now let me write what is given. So I1, okay, I don't remember. What's the value of I1? 5 amps. Right. I2 is 2 amps. And distance between these two wires is 6 centimeters. So that's effectively what is given. And now we need to answer the question. Actually, we need to find a point where the net magnetic field created by these two wires will be 0. Right? So basically we have this current creates magnetic field everywhere. The whole space will be filled with magnetic field. This current creates magnetic field which fills up the whole space. And we need to answer the question, are there any points on this line, actually, on this line? Are there, almost erased it, sorry. Right. So are there any points on this line where magnetic field, net magnetic field is 0? Okay, so first of all, we need to first conceptually discuss in which region that is possible, and then we will start we'll start targeting that particular region in terms of finding that particular desired point, right? So and in order to discuss conceptually, first we need to see directions of the magnetic fields, direction of magnetic field B1 and direction of the magnetic field B2. It's in this case, in order to find a direction, we just need to we need to use a right-hand rule number 2. Okay, so outstretch your thumb in the direction of the current and curl your fingers around the wire. So let's do it for wire number 1. So it is into the board, so I have to position my hand like this and curl my fingers like that. So it means that magnetic field lines are going to be form that. You know what? Let me use something. You know what? Let me try do it by hand. Okay, decent circle, decent. Not the best, but decent. And direction this way, clockwise. So here it will be this way, that way, and then this way. Let me check if I got, yeah, that's the correct direction. And now let's do the same for the green one. All right. And so now direction of this circle, now I have to curl it like this, my fingers, so out, and that is counterclockwise. Right. So that's magnetic field lines of green wire. So between the wires, of course, magnetic field, you remember, tangent to the magnetic field lines, so that is B2. And of course, magnetic field created by the blue wire will be this way. B1, not B3, sorry. B1. So immediately, so the question, is it possible to get 0 net magnetic field in the region between these two wires? Of course, impossible, right? Because both magnetic fields are parallel to each other, right? They're going to increase So the net magnetic field is going to be stronger than B1 or B2. Pretty much here, cancellation of the magnetic field is impossible, right? So let me draw this line, and over here I can write that this is B net equals 0 is impossible. B net equals 0 is impossible. Right. You see? Again, if something not clear, tell me. So it means that now there are only two regions. This region and that region, right? So what about this region? So magnetic fields, of course, will be in the opposite direction. This magnetic field created by the green, imagine just a big magnetic field line, right? And over here it is going to give us green magnetic field will be B1, right? But it will be weak because it's kind of farther away from current I2. And I1 at this point all the time is going to be, in the opposite direction, but it's going to be stronger all the time. So this will be B1. Oh, this is B2. Sorry, this is B2. Right. So in this part, in this region, on this line, right, B1 is going to be stronger all the time because current is larger. You see I1, I1 5, I2 2. Right. So in this part, magnetic field created by the first wire is going to be larger all the time than B2. Again, here, cancellation of these two magnetic fields is impossible. Cancellation of these magnetic fields is impossible, right? So let me write something like what I wrote in my notes. So B net equals 0 again is impossible. Right, okay, let me separate it like this. Since B1 is larger than B2 all the time. So it means that there is only one region left over here. And here, it's possible because in this case, I2 current is smaller than I1, right? So it means that magnetic field created by I2 kind of smaller, but points are closer to I2 than to I1. So in this case, it's possible to find the spot with the net magnetic field equals 0. Right? So here, B net equals 0 is possible. Is possible. So now let's find it. And so let's just assume that magnetic field is 0, for example, at some arbitrary point at the distance x. So I introduced basically a variable, unknown. And balancing these two magnetic fields, I should be able to find the value of that x. Right? Okay, so, and you know what? First, let me draw also magnetic field line created by this blue wire at this point. Green magnetic field we can see, but magnetic field created by the blue wire will be some sort of like this long, circle with very large radius, reasonably large. So, and the magnetic field, this will be our B1, right? And B2 will be this way. And of course, at this point, these two magnetic fields in absolute value must be equal to each other, but of course, opposite in direction. Right? Okay, so now let me write the expression for B1. B1, absolute value. And of course, we need to use this formula. So it will be equal to mu naught times I1, right? I1, and divided by which distance? Because distance from this point to the source, this distance, which is d plus x. D plus x, that's the distance. So it will be d plus x. Now let's write expression. So that's the strength of this magnetic field. Now B2, strength of this magnetic field. So it will be mu naught times I2 divided by what? By the distance from the source 2 to the point in question, right? So that distance, of course, x, it's our unknown x. In this case, it's a 2 pi times x, right? And these two strengths must be equal. because that's the condition which we want. That's the condition for the point which we want to find, right? So B1 must be equal to B2. Of course, that's at x, right? Okay, so now let's equate them. And you know what I will write underneath, because I'm running out of space. Okay, let me rewrite B1 equals to B2, and let's write, so that is mu naught I1 divided by 2 pi d plus x, just this, and then equal to mu naught times I2 divided by my whiteboard started wobbling a little bit, need to fix it, 2 pi times x. Very simple equation. How many unknowns in this equation? 1x. We can cancel mu naught, of course. Right, mu naught goes, 2 pi goes, and I1 is given, I2 is given, d is given, x is unknown. One equation, one unknown. We can solve it. So from here, let me rewrite without those constants. I1 divided by d plus x equals to I2 divided by x. Simple equation. X goes over here, d plus x goes to there. And let me flip also the equation immediately. So it will be, no, I'm not going to flip it. I'll just write it the way it is. So I1 times x equals to I2 d plus x. Just simple mathematical manipulations, right? So now x is over here and x is over there, so that x with I2 must be moved to that side, right? So it will be I1 plus I2, not plus, minus, sorry guys. Since here we have it with plus, if I move it to that side, it will be with minus. Minus I2 times x equals to I2 times d. Okay, so that's our unknown. Let's solve it for x. So x equals to I2 times d divided by I1 minus I2. Okay, so that's algebraic solution. All right, and now we just need to plug numbers. So I2 is 2 amps times 6 centimeters, that d, distance between wires, and this will be I1 minus I2, so it's a 5 minus 2. 5 minus 2 amps, and we're getting here 3, canceling with that, we will get here 2 times 2, 4 centimeters. So that's the answer. At the distance 4 centimeters from second current, there will be point of 0 net magnetic field. Right? So pretty much, again, the goal was just to practice this formula and finding the right-hand rule. And sort of mathematically, we just need to balance magnetic fields. Right. Maybe at some point I move this problem to, to our recitation classes. Mm-hmm. Any questions?
Yeah, I have a question.
Yeah.
I'm still confused, like, why did you choose for B1 the distance as d plus x and for B2
Yeah.
just the
Okay,
x?
okay, 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 okay. Look, this R is the distance from what to what? Distance from the current, from the wire, from the center of the wire, to the point in question where you want to find magnetic field, right? That just by definition, the way we derive it, you see, from the wire to the point in question. Now, we have two currents. So B1, so this distance R should be from I1, that's the current which creates the magnetic field B1 at this point, right? So this distance, this is our distance R. So this distance R, right? From I1 to the point in question. So this distance is what? D plus X. See that?
Oh, okay. Yeah, correct.
If you still, I can draw here additional picture underneath. So blue, yeah, it was blue. So that is our wire I1, current I1. So basically, I can draw you a bunch of magnetic field lines all the way to this point. That is our point in question. So of course, you need to know this distance r, right? Which is d plus x. But for the green wire, the situation is different because green wire is over here. So you need to draw again. I can draw a few magnetic field lines. So for the wire 2, we need to know again the distance, but now from this green wire to the point in question, it's this distance r, which is in our case x. You see, the answer is in the definition of r. It's a distance from the wire to the point in question. Since we have two wires, we have two different distances, but to the same point. The point in question is the same. So for the first wire, it's this is R1. For the second wire, this is R2, which is X. See it?
Yeah, I got it now.
Okay.
I'm clear.
Okay.
Yeah, thank you so much.
Okay. Cool. Yeah, actually, I found this problem, and I think it's nice. Maybe next semester I will move it to our recitation classes. Enough of this formula because we have tons of other stuff. Now let's quickly discuss Ampere's law a little bit. I don't want to find magnetic field by an infinitely long wire. We've done it in our recitation classes, in the lectures. You can refresh it by yourself. I just want to discuss quickly Ampere's law in general and answer a couple of questions conceptually. Okay, I'll erase this now also, and now 2, and that's conceptual question. What if we have these 3 currents? Okay, I will use the same color. Current number 1 out of the board, basically infinitely long wires parallel to each other, but currents are in different directions, and they have the same values. Currents are of the same values. So let's say this is I1, then this will be, let's say, I2, then I3, and I4. They are all of the same value. So let's say I1 equals to I2 equals to I3 equals to I4 equals to 2 amps. And you remember what is the first step in any problem about Ampere's law? You need to pick an Amperean loop, which is a closed loop, any closed loop, right? So let's say somebody pick an Amperean loop for us. Which one? This. Okay, that's our Amperean loop. All right, so let me say it's a amp loop, Amperean loop. Then the next step, usually after you pick an Amperean loop, what do you need to do next? Because you will have to integrate this integral b dot ds, this line integral over the closed loop, right? So of course, whenever you integrate over a line, you need to pick a direction. Are you integrating clockwise or counterclockwise, right? So let's say we pick a direction, and that direction is clockwise. This way, this way, this way. So that's the direction of integration, right? And now the question is, we need to find what we need to find. Very simple. We just need to find the value of that integral, b dot ds. Just the value of this integral. It looks like soon I will have to change marker. Right. Okay, so according to the Ampere's law, instead of calculating this integral, we can just do what? We can calculate all enclosed currents, multiply it by our universal constant mu naught, and that's it, right? So it simplifies. In this case, you don't have to do actual integration. So equals to, okay, let me write that. That's what we need to find, basically, right? Find the value of this integral, right? So it is equal to mu naught times I enclosed. And now you remember which currents are positive and which currents are negative in Ampere's law once you pick a direction of integration. It's you need to apply right-hand rule number 2 sort of in the opposite direction. So in the reverse direction. So you need to, you see this direction of integration, you need to curl your fingers in that direction, right? And your outstretched thumb gives you positive direction for the current, for a current. So again, curl your fingers in this direction in this direction, and your outstretched thumb gives you positive direction for the current. Right? Okay, let me draw something ugly. 4 fingers and then this, right? And this, let me show that this is into the board, into the board, right? This direction. So that's the positive direction for the current, positive direction for the current. So in this case, into the board only I2. It means I2 current is positive, I1 is negative, and I3 is negative, right? So I can write this as mu naught and minus I1 plus I2 and minus I3. And since all of these currents are 2 amps, so it's a mu naught minus 2 amps plus 2 amps minus 2 amps. So of course, this and this cancel, and we have a negative value of that integral. So we will get, as a result, it is equal to minus mu naught times 2 amps, right? So that's the value of this integral, right? Sort of conceptual question. No, it's a question which is a worth of which can be on in the first problem among the multiple choice questions. Right. Just quickly check the if you're familiar how to apply Ampere's law. Right. We can also look at this situation. What if Amperean loop is this? What if an Amperean loop is this? You remember you can use for any Amperean loop. Ampere's law can be used for any Amperean loop. In the direction, let's say this direction. So now let's say this is our Amperean loop. Basically part B, let's say for part B. Amperean loop for part B, and that is Amperean loop for part A, for example, right? So now, so how can we find this integral for part B? So it's part A and now part B. So integral of B dot ds again equals to, again, mu naught times I enclosed. And so we just need to write all the currents which are enclosed. Actually, I should have mentioned also current I4 is not enclosed for part A because that is outside of the chosen Amperean loop. So we didn't include it into these calculations. Only currents within an Amperean loop. But in part B, all currents are enclosed. So now, of course, we need to write them all. We need to use them all. But before I start writing them, of course, I need to make a decision which currents are positive and which currents are negative. So again, I curl my fingers in this direction now, and you see my thumb now is out of the board. So it means that currents out of the board are positive for this situation. So out of the board, I1 and I2. So these currents are, I1 and I3. So these currents are positive, but I2 and I4 negative. So it will be I1 positive minus I2 plus I3 minus I4. And since they're all of 2 amps, of course they all cancel each other, right? So again, this is basically 2 amps minus 2 amps plus 2 amps minus 2 amps, right? So of course, that is just 0, right? So the value of this current, the value of this integral will be 0 now, right? So now integral of b dot ds equals to 0 in part b. Okay, I just wanted to refresh which currents do we call? We call as an enclosed currents, which currents are positive, which currents are negative, and so on. But I don't want to, again, solve problems about finding magnetic field created by an infinitely long straight wire. Here in my notes, you can find that example or not. And plus, you have in your notes recitation classes notes, and lecture notes. So enough of Ampere's law. I just wanted to discuss a couple of conceptual questions. That's it. Now, after that, we move to the magnetic forces. So now let's solve first conceptual question, two conceptual questions, and then a problem about magnetic force. First, conceptual questions will be about magnetic force on a point charge, and then actual problem about force acting on the on a piece of wire, exposed to the magnetic field. Right? Okay, let me get some water. Okay, so we have an infinitely long straight wire. You know what? Let me put part A, and infinitely long straight wire. Of course, with a current. Current which way? That way. So let's say current that way. The value of the current doesn't matter because we just want to find directions of the magnetic forces. So that's the that's the current, and now we're going to drop a few point charges. And of course, those point charges must move, because if a charge is stationary, right, stationary, exposed to the magnetic field, it is not going to experience any magnetic force. As I told you again, everything in magnetism, everything is in dynamics. Charge must move. If it's stationary, it wouldn't experience any force. So let's start with the first point charge over here. Okay, let me grab my notes. So positive charge Q, right, and it travels, let's say, this way, V. So we need to find magnetic force. Let me write, so what needs to be found? So F, directions, because there will be several particles. And so since, yeah, again, it's just a fundamental process, and we have a fundamental equation describing this process, right? So let me just write down here the formula. F equals U and V cross B, cross product, right? Okay, you know what? Maybe I will write underneath. So absolute value, in order to find absolute value, it will be QVB times sine of the angle between V and B. And then direction can be found using right-hand rule number 1, right? Okay, so in order to find direction of this magnetic force, of course, we need to find first the direction of the magnetic field. And of course, that magnetic field is created by this wire, right? So of course, magnetic field lines are going to be circles. All right, directions, right-hand rule number 2, outstretch your thumb, curl your fingers around. So above it will be out of the board, dot. So magnetic field, let me write above over here, dot, 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 right? So these are magnetic field, right? And below it will be into the board, right? So into the board, cross, 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 cross. Okay, enough. B. So now we have all necessary vectors in order to find a vector representing the force. V cross B. V that way, B out of the board. So you remember right hand rule? Okay, so there's some questions. Guys, it's better if you just say it, because I don't look at the chat. Is this practice session be recorded? Yeah, it is recorded right now. All right, if everything goes fine, so then of course I will post it on my YouTube channel. Right. Yeah, it's being recorded. So right hand rule. First, you need to align your hand in the direction of the first vector in the cross product. Then you need to orient your hand in such a way so that you can naturally bend your fingers in the direction of the second vector, right? So V that way, and then vector B is out of the board towards you. I have to position my hand like this, orient my hand like this, and now I can naturally bend my fingers towards you. And as a result, that is the cross product, V cross B. And the question is it the whole story or not? In the lecture, I told you that in this case, finding a direction, correct direction, consists sort of like a 1.5 steps, 1.5 steps. The first, find the direction of V cross B. And then quickly look at the sign of the charge. If that charge is positive, the direction of V cross B gives you direction of the magnetic force. But if that charge is negative, then you need to flip that found direction of V cross B, and then flip it. So don't forget about that flip, because it's a very, very common mistake. So quite often students remember that, but in the middle of the exam, somehow they forgot. Quite often they forget about that, right? So don't. Right. So in this case, charge is positive, so it's fine. So direction of V cross B gives us direction of the force. So V cross B, force is down towards the wire. So the force will be this way. Okay, I use red. So that's the direction of the magnetic force, Fm, magnetic force. Right? Now, the second charge. Let's drop the second charge over here, and it's a negative charge, minus q. In direction of the velocity, let's say it moves up, v. And again, guys, make sure that you're comfortable with using right-hand rule number 1. Otherwise, you will struggle in the exam a lot. You will struggle a lot. Right? So, v up, magnetic field out. So I have to position first my hand like this, right? And then bend my fingers towards you, right? And as a result, this is direction of V cross B. Let me write it in black. So that's the direction of V cross B. But the charge is negative. So we need to now apply that additional half a step. So this is the direction of V cross B, but since charge is negative, so we need to flip that found direction to the opposite one. So the direction of the force will be the opposite. That's why I use black vector to show that direction. So this will be direction of the actual force. Right. So don't forget about that. Okay, so there are two other situations, right? But you see, I think it's enough, right? We're just refreshing, reminding you there are two other charges. You can look at by yourself, right? Maybe you know what? Let me look at negative charge. Let's say here there's another negative charge, value q, and let's say it moves this way, v, right? Yeah. So now we need to find direction of the force. Again, first v cross b, v that way, b into the board, so v cross b, you see, v cross b. So v cross b is down. But since the charge is negative, so the force will be actually up. So let me show both directions. So v cross b is down again. V cross b is down, but the force is going to be up because that is the negative charge. Don't forget about that. Great. But again, if you need more, tell me. And if you still struggle with the right-hand rule, send me a message. We can, I don't know, set the meeting and we will, like virtual meeting, or maybe at school, right? Next week I will be, of course, at school, right? And we can practice that. So now another conceptual question, B, part B, and it's this. Let's say we have magnetic field represented by the dot. It means that uniform magnetic field, it means out of the board. Let me draw a few of these dots. Oh, it's so annoying. Right, so B, enough. And now let's send a couple of particles into this uniform magnetic field. All right, so first one, let's say it enters this way over here. That's V, okay, just V. Oh, let's call it V2. So charged particle and yeah, charge particle, and we actually don't know which particle is this, positive or negative. But we do know that, actually, do you remember what happens? Which trajectory are we going to observe in this situation? You remember two cases. If you send a particle along magnetic field lines, particle is not going to experience magnetic force because V cross B, angle between them is 0 degrees, sine of 0 degrees is 0. So if you send particles along the magnetic field lines, it will move along a straight line. If you send the particle, for example, into the board or out of the board, it will move along a straight line. But if you send the particle perpendicular to the magnetic field lines, which trajectory are we going to observe? We spent, you remember, one of the recitation classes discussing this type of motion. It has a very cool name, cyclotron motion, right? Cyclotron motion. It's just simple circular motion, but cyclotron sounds cool, right? So in this case, since particle moves perpendicular to the magnetic field lines, it is going to experience cyclotron motion along a circle. So let me draw that circle. And let's observe that this circle was, okay, distorted circle. Let me make it look better. All right, so that's the circle. Let me add additional line of dots. Right. And so now, if you know this circle, direction of the, okay, yeah, this trajectory, can you tell me, is this charge a positive charge? Is this particle positively charged or negatively charged? Typical question on my exams. Quite often I ask a question like this. And the answer is quite simple. So it's all about this formula, QVB. When you see a trajectory, can you tell me what's the direction of the force? Easily. You can easily tell me. Because it bends this way, so it means that force at this point, that way, at this point, this way, that way, right? The force is towards the center of the circle. So the force, okay, I will use this point. The force is this, Fm, magnetic force, that way. So we know direction of F, and now we just need to find direction of V cross B. And if this direction is the same as the force direction, then what should be the sign of the charge? Of course, it must be positive, because direction of this and direction of that are the same. So it can be only when the charge is positive. But if direction of the force and direction of V cross B are opposite, it can be only in one situation, when charge is negative. So pretty much that's the argument that you have to apply, or reasoning that you have to apply in order to get to the conclusion. Charge positive or charge negative. In this situation, so now let's find the direction of V cross B. V that way, then B out, B is out towards you, so I have to orient my hand like this. And in this situation, I can bend my fingers towards you. So V cross B, and the V cross B is down, right? So I can draw that this is V cross B. So directions are the same, force and V cross B, so it means that this particle is positively charged. So let me write that down. Okay, so let me label it Q2 because there will be second particle. So Q2 is positive since directions are the same. And now let me send the second particle, actually the first one. And let me add additional line of magnetic field lines. Right, so, and the particle now enters over here this way. So that's V1. And the particle with the charge Q, which again we don't know if this this charge is positive or negative. We don't know, but we observe its trajectory. I know bubble chamber, photograph from a bubble chamber or cloud chamber. So let's assume that we know that trajectory is this. So immediately, since you see the trajectory, you can tell immediately that force acting on this particle is that way. Fm, magnetic force, because that force bends the trajectory in this circular one. And so now let's find V cross B. V is up and B is towards you. I have to orient my hand actually like this, right? So V cross B, you see, B towards you. And my thumb gives me the direction of V cross B. So V cross B is that way. You see, directions are opposite. Force that way, but V cross B that way. So it's only possible when this charge is negative. That's basically how elementary particles, physicists, engineers, right, determine the sign of charges. So in this case, Q1, Q1 is negative. Right? Okay, several times in the past I gave problems like this among multiple choice questions. I can give 2 particles, 3 particles, can vary directions, right, of particles and directions of the magnetic field, but logic is very simple. It's all about, in this formula, compare directions of force and direction of V cross B. Make sense? Awesome. But if you're not screaming, then I take it as yes, it makes sense. But again, logic is not that complicated, right? You just need to be familiar, right, and practice a couple of times. Not that bad. Okay, so now next problem, number 4, and now this will be the problem about using this formula, IL cross B. Okay, I need a nice picture, and you know what? I will draw probably in this corner. So let's assume that we have a wall. You know what? No, I will draw it here. So a wall, right? And 2 springs are attached to this wall, and those 2 springs are connected to the same infinitely long straight piece of wire. Right, let me draw it like this. So we have a spring, and here the second spring. And here I have an infinitely long straight piece of wire with the current. Okay, let me. Current is this way. I. Actually, we have a freedom. We can turn that current on. We can turn that current off. Right? Okay, then. It is exposed. Yeah, spring constants are given. So K. Springs are identical. Right? Then this wire with the current is exposed to the uniform magnetic field. Actually, length L of this wire is exposed to the uniform magnetic field. So let's assume that magnetic field is in this region. Right, and the width of this region is L. I know, 20 centimeters, I think. 20 centimeters, yeah. Actually, it looks ugly. M, let me change it. 20 centimeters. And magnetic field is out of the board. Dot, dot, dot. And let me draw a few more dots. So that's magnetic field, and the value of that magnetic field is, I don't remember, 0.5 Tesla. Quite strong magnetic field at 0.5 Tesla. Then what else is given? Let me check. Okay, so now, yeah, the values of K are given. So K equals to 10 newtons per meters. Values of K are given. And there is another parameter given, but I need to discuss what happens over here in terms of physics in order to introduce the second given quantity. So guys, this is situation when the current is on. And actually, eventually, we will have to find the value of this current. But if you turn this current off, what happens? This wire will be moved to this position. Pretty much it will move to the point where these two springs are unstretched. Because right now, these springs are compressed. But if you turn this current off, this wire is going to be over here. Let me draw that line with the dashed line. So that's pretty much position of the wire when the current is off. Let me write it down. All right, so position of the wire when I equals to 0. But once you turn the current on, of course it will start experiencing magnetic force, and that magnetic force will push it that way, compressing the spring, working against spring forces, pushing in the opposite direction. Right? So that's the situation, and this amount of compression between this point where the current is 0 and the point where the current is, which we need to find, that compression is given. So this compression is where I showed it. Let me show it here. So this is delta x, and the value of delta x is given, and I don't remember what's the number, 1 centimeter. 1 centimeter. So guys, effectively, this system can be used as an amp meter device which can be measure current. For example, if you calibrate this distance, right, this length, right, for example, this is 1 amp of current. So then when you turn the current on, and if the wire is over here, then it's 1 amp. Then, for example, 2, 3, and so on. So basically, if you calibrate it properly, this device can be used as an amp meter, right? And so the question is, we need to find the value of the current. Okay, with this compression. So let me check if something else I missed. It looks like everything is here. So now, before I start discussing it, discussing physics, right, and what can be applied, let me introduce coordinate system. Let me introduce coordinate system. So let me introduce x-axis this way. Right, so this is x, right? And I'm going to position origin at this point. So this is x equals to 0. So pretty much at the equilibrium when the current is off. So that's my 0 point origin, right? And of course, this is delta x, right? Of course, first we need to answer the question sort of globally, conceptually, right? So which equation or equations can be used here? And then we will start diving into some gory details, right? So look, in this case, we don't have any motion, right? It's a static equilibrium situation. And static equilibrium problems you discussed at the end of Physics 1 course in the previous semester, right? And usually students don't remember which equation must be used to discuss static equilibrium most of the time. So I usually guide in this way. Guys, which equation, fundamental equation, can be used to describe motion of any system, And students from my recitation classes, they probably remember this question because I bug them quite often. Okay, you all know that law. You all know that equation which I'm asking. It's a Newton's second law. That's the meaning of Newton's second law. It's an equation which allows us to describe motion of any classical system in the universe. It doesn't matter if it's a binary star spinning or cars driving or cat is running. It doesn't matter. Grab Newton's second law, apply, and you should be able to describe that motion. So that's to describe motion. But in our case, there is no motion. Can we apply the same law to describe no motion situation, static equilibrium? Of course. We just need to apply what? We just need to set acceleration to 0, because that's if you have static equilibrium, no motion, acceleration is 0. And you're getting the equation which needs to be applied. Net force acting on the system equals to 0. That's the beginning of the solution. And then from there we will start diving deeper and deeper, but everything in this case starts from the Newton's second law, effectively, right? Okay, so now let me write what I just blabbed. So any motion can be described using Newton's second law. So effectively, sum of the forces acting on the system equals mass times acceleration. But in our case, acceleration equals 0, right? In our case of no motion, because what? We turn the current on, and of course magnetic force will push or pull, it doesn't matter, right? This wire to this position, and it will stop at this point. So no motion, acceleration equals 0. As a result, we're getting the equation which needs to be used. So sum of the forces equals to 0. So that's the beginning of the solution. Of course, forces acting on the wire, So now you see what needs to be identified. We need to draw all the forces acting on the wire, write them properly, and balance them. And from there, we should be able to find unknown, which is current in our case, right? So now let me draw all the forces. Spring force. Since these springs are compressed, this and that, of course, they're going to exert two spring forces trying to move this wire back to the equilibrium. You remember spring force from physics 1, right? So of course, this will be F spring, and this will be also F spring from the first wire and from the second wire, or from the first spring and from the second spring. But of course, there is a second force, magnetic force. And of course, that force must act this way. But let's check quickly if we're getting that force. So of course, we need to use the expression for the magnetic force, which is ILB. All right, so let me write it over here. F magnetic equals to I and the cross product of L and B. Direction of L, it's a direction of the current. So cross of a direction of the current down, and B is towards you. So how can I position myself in order to get the correct direction? So current is down, L is down, so I have to position my hand like this, right? And then, I have to orient like this. So I can bend my fingers towards you, because magnetic field is towards you. So L down, and that towards you. And as a result, magnetic force, you see my thumb points that way. So that's the direction of the magnetic force. And it makes sense because that magnetic force must balance these two spring forces. So that's the direction of the magnetic force, Fm, magnetic force. So these three forces, nothing else. Okay, there's no gravity. Or we can say it lies on the horizontal table, right? And if there is a gravitational force, then it is just balanced by the normal force from the table. So they just balance each other in the vertical direction, and nothing changes in the horizontal direction, right? So now, and this is our positive x direction. So this force and this force are positive. This force is negative, right? So I will write, so F spring plus F spring minus F magnetic equals to 0. So, balancing forces. Let me write this explicitly so that I can use over here. Of course, spring force is just a K delta X. But you know what, let me write this. Absolute value of M now, because we know the direction. I already used minus over here, so now I just need to know the absolute value, magnitude of this force, magnetic force. So L and B, L down, B towards you, so the angle between them is 90 degrees. Magnetic field towards you, L is down, so the angle between them is 90 degrees, right? So it will be, all right, I, L, B. So let me emphasize that L is perpendicular to B. Right? So that's the expression for the magnetic force, ILB. And of course, expression for the spring force, K times delta X. Delta X compression is given. And of course, we have these two of these forces. So pretty much we're almost very close to the end. So now let's just use those magnitudes. So it will be K times delta X plus K times delta X minus I L times B equals to 0. So we got the equation. How many unknowns do we have here? K given, delta X given, I that's our unknown, L given, B is given. So pretty much one unknown only, right? So that is our question mark unknown. So let's solve it, and that will be the problem. So ILB equals to 2K delta X. So I combine these two forces and move them to different sides of the equation. So from here, I equals to 2K delta X divided by L times B. Let me check if I got the same. Yeah. So that's the expression. And now numbers are given. You can plug them. Of course, centimeters must be converted into meters. Right? So this must be in meters. Meters, so don't forget. And I'm not going to plug numbers. I will just write down the answer immediately. 2 amps, significant current. So 2 amps of current. Mm-hmm. Yeah, it's the weirdness of the virtual classes, right? That there's no feedback, not much. Right? And also when you run classes with the masks on, again, faces are barely visible, right? So also kind of a little bit awkward since you don't see reaction on faces, students'
I have a
faces. Yeah.
question. Does it say change of x or is it change of r where you circle in green at the final solution?
Delta x must be in meters.
Okay.
Since delta x given in centimeters, right? And quite often I see students, they just grab whatever number is given, plug it, and of course, as a result, it usually mass of the units. Because you see, K is newtons divided by meters, so of course it means that immediately everything must be in meters. Otherwise, it will be confusing mess for people who would try to understand what you wrote. Mm-hmm.
Yep.
Awesome. Okay, enough about magnetic forces. So magnetic force on a point charge, magnetic force on a current, straight current, right? So I don't think we solve problems calculating force on a wire with overcomplicated shape. I don't think so. It's more challenging mathematically. So now next, Faraday's law and Lenz's rule. First couple of conceptual questions and then a problem. So Faraday's law, right? So let me first conceptual, two conceptual questions I will combine in question number 5. So what if we have this situation? Let's say, okay, let me create a big ceiling, and let me hang 3 conducting loops. All right. First loop will be swinging from side to side. Second loop will be oscillating up and down, and the third loop will be spinning. Right. So let's discuss all these 3 situations in order to see, are we going to observe any induced EMF in these loops and induced current, right? Faraday's law. Okay, so first I need to draw magnetic field lines. Okay, which out? So out. So these are magnetic field lines. So B, enough, right? And then there is a loop. First, in the first situation, that loop is oscillating from side to side. And of course, assuming that there is no border of the magnetic field, right? So pretty much this magnetic field extends all the way to that infinity, for example. So pretty much when it oscillates, it doesn't get out of the magnetic field, right? So, and of course the question, are we going to observe any EMF or induced EMF or induced current? In order to answer this question, of course, we need to analyze what? We need to analyze magnetic flux. And then, if magnetic flux is constant, then the loop conducting loop is not going to do anything. Because if the magnetic flux is constant, doesn't change in time, then EMF will be 0. EMF 0, induced current 0. Right. So let's analyze. So 3 parameters, B, external magnetic field, A, and the angle. As it swings from side to side, magnetic field, nothing happens to the magnetic field, it's constant. Then area of the loop, we don't change the area, it stays the same, right? And the whole loop is exposed to the magnetic field, right? So area is constant also. And the angle, of course I can, for example, choose my area of vector out of the board in the same direction as the external magnetic field. So the angle is 0, but anyway, constant. 0 degrees, but anyway, constant. So if all these constants, then of course magnetic flux will be constant. Because the magnetic flux is a B dot A, B times A times cosine of angle between them. Right? So 3 parameters are constant. So of course magnetic flux is constant. And of course, as a result, induced EMF is 0. And of course, current is also 0. So in this case, there wouldn't be any current flowing in this loop. 3 parameters, B, A, theta. So in this case, you know what? Let me erase this because I wrote it underneath. So no current, no induced current. Right. So now, second situation. What if we have this string and then there is a spring? It's not an inductor, just a spring, right? All right, with some spring constant K. And then there is a loop, our loop. So pretty much this loop moves up and down. Effectively the same story. Again, B constant because it doesn't, as it moves, magnetic field doesn't change in time. So let me write it over here. And yeah, B is constant. Then area of the loop, again, constant. We do not distort that loop, so it's a constant. And then angle, again, if I align my area vector in the same direction as the direction of the external magnetic field, angle will be 0. If you align A into the board, it will be pi, but anyway, in both cases, angle is constant. So as a result, flux is constant, and as a result, no induced current or no induced EMF. So no induced current, I induced, no I induced. And the last case, what if I, which way I drew it? Over here. Right, so again the wire and now the loop, and the loop is spinning this way. Right, spinning along the vertical axis. So in this case, all right, so B external again still constant, area of the loop still constant, we don't change the area is constant, but what about the angle? The angle changes. Let me show it to you. Right, so let's start with this situation. So magnetic field is towards you, right? And so let's say my area vector, this A, is also at the initial moment of time towards you. So along the magnetic field. So angle is 0. And then once you start spinning, so now it's 30 degrees, 60 degrees, 90 degrees, 120 degrees, 150 degrees, 180 degrees, 270, 360, 540, and so on. So as you keep spinning, angle keeps changing, it keeps increasing, and increasing. So angle in this case changes, right? Angle between the magnetic field and the area vector, so changes. So a theta changes, actually growing. Right. So as a result, of course, here, yeah, there will be magnetic, there will be induced EMF. So EMF induced is not 0, and of course there will be I induced in this case. Just a fact that there is a current or no current, this part, right? So now part B, and again, guys, if something is still not clear, tell me. So part A, part B now. It's sort of similar to your quiz, right? The last one, quiz number 7. But anyway, since some answers were okay, not correct, let's say. So it's worth of discussing. So let's assume that current is constant flowing through this wire, infinitely long straight wire. Current is constant. And of course, we can draw, of course, magnetic field created by this wire. Again, right-hand rule number 2, magnetic field lines are circles, right? So, and outstretch your thumb in the direction of the current, and here magnetic field will be into the board, it's cross, and on that side will be out of the board, dots. So here it will be cross, cross, and here dot, 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 and dot. So that's B. Okay, external. And now let's assume that there are 2 loops, and we're going to drag them in a certain directions. So first let me drag the loop this way, V. And the question is, are we going to observe an induced current in this situation? So the answer is, again, we need to analyze 3 parameters like what we did here, B, A, theta. Let's start with A. Area of the loop stays the same. No troubles from that side, right? So then angle. Of course, I can position, for example, area vector also in the same direction as the direction of the external magnetic field. So angle will be 0, but anyway, constant. So it is not going to change our magnetic flux. Then what about magnetic field? Magnetic field. And some students here, not confused, but not completely confident. Look, guys, magnetic field, of course, changes in space. For example, if you look at this point, magnetic field here stronger than magnetic field at that point, right? Or that point of the loop, because it's closer to the source of the magnetic field, to the wire. Of course, magnetic field here stronger, magnetic field there weaker. And then if you move farther away, of course, magnetic field getting weaker and weaker and weaker. Magnetic field changes in space. But who cares? Actually, Faraday's law doesn't care if something changes in space. Look, it only cares if a magnetic field, and of course, as a result, magnetic flux, changes in time. And in this case, magnetic field, and then, of course, as a result, magnetic flux, they don't change in time. Look, if I take, for example, again, this point, right? So let's say at the initial moment of time over there, let's say 1 Tesla magnetic field. And if you drag this loop that way, parallel to the wire, along the wire, of course, that magnetic field at that point will be exactly the same in time. So if you move it here, right, the loop, still 1 Tesla, still 1 Tesla, 1, 1, 1, 1, and you keep moving, you see magnetic field do not change in time. It changes across the loop in space, but who cares? Actually, Faraday's law doesn't care if it changes in space, right? So nothing changes in time. In this case, flux is constant and there is no induced magnetic field and there is no induced... Wait, what did I say? Induced magnetic field? Actually, there will be induced magnetic field, but no. Conclusion about the induced EMF and induced current. Right. I need to watch closely what I say. Right. So in this case, nothing happens. So let me write that. So I induced in this case, I induced equals to 0. But let's change the direction of this motion. So let me position now the loop over here and move it out away from the source of the magnetic field, away from the wire. Now, yeah, magnetic field now will start changing. Still, area of the loop stays the same, like what we had here. Again, angle will be, again, let's say area vector into the board. So angle will be 0, but anyway, constant. But now what happens to the magnetic field? Again, magnetic field still changes in space, because magnetic field over here will be stronger than magnetic field over there. But now, as you drag this loop away, so if you take, for example, this point in the loop, so first magnetic field will be here, let's say 2 Tesla. Then if you move the loop over here, actually I have a loop, I can show it. So let's say first you are here, you use this point. So first here, magnetic field 2 Tesla. As you move it, it goes down 1.5, 1.8, 1.7, 1.5, and so on. As you keep moving, magnetic field keeps moving down in time. In time. So now magnetic field changes in time, and of course flux changes in time, actually going down. So now we can apply actually Lenz's rule in order to find the direction of the induced current. And I am thinking where I can fit that. I think underneath. Yeah, you can see it. I can fit it here. So 3 parameters. B external for this case. B external, as we move away from the source of the magnetic field, of course, is going down, getting weaker and weaker and weaker because we move farther and farther away from the source. B external is going down. Then our area stays constant and angle also stays constant. Angle also constant. So as a result, we can combine these 3 pieces of information into the expression for the magnetic flux. Of course, flux is going down. So magnetic flux is going down. And as a result, what will be the response of the loop? You remember, according to the Lenz's rule, loop doesn't like when flux changes. In this case, flux is dying, so the loop becomes supportive and behaves like Florence Nightingale, helping supporting dying flux. So it will start driving current in such a direction so that the induced magnetic field is in the same direction as the external magnetic field within the loop, because it supports flux within the loop. So it means that over here within the loop, in the same direction, it means I can draw a bunch of crosses representing B induced, right? So over here I can write, so B induced is in the same direction as B external, right? And now right hand rule. Okay, let me move up. Right hand rule. So that's our loop. Induced magnetic field is into the board, right? So I have to position my hand like this, right? You see, like this, into the board. Because if I position like this, it will be out of the board. So like this, into the board, and my thumb, outstretched thumb, gives me direction of the induced current. So which is clockwise direction, right? Clockwise direction. Let me check if I got the same. Yeah, in my notes, the same direction. So clockwise direction, so that's I induced. And of course here, I induced. So over here I can write, so I induced in a clockwise direction using right hand rule number 2, basically. I almost guarantee that there will be problems, of course, and questions about Lenz's rule. So you have to be comfortable. And of course, every time I will ask, justify, explain, right? So analyze 3 parameters, get information about the flux and direction of the magnetic field, induced magnetic field. And then once you know the direction of the induced magnetic field, apply right-hand rule to get the direction of the induced current. Okay, so that's the conceptual questions which I was planning to discuss, and now let's actually solve the problem, big problem about Faraday's law. U-shaped rail. Actually, in the lecture I didn't solve that. We solved something similar in the recitation classes, but not U-shaped rail, and I'm going to make it slightly more complicated than usual. It's a classical problem, but I added some flavor. All right. Let me write, so U-shaped rail, U-shaped rail. So what do we have here? So first, rail like this, then this, and then, you know what, let me make it wider. I just realized. So U-shaped conducting rail. So it's made of metal. Width is given L. Actually, I also introduced numbers. Oh, okay, why not? So L equals to 0.3 meters, I think. Yeah. Then the whole structure is exposed to a uniform magnetic field, external magnetic field, out of the board. So let me draw a bunch of dots out of the board. So B, 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 and maybe here a few dots. So that's B external. And the value of this magnetic field is given 0.2 units of Tesla, of course, right? Then, of course, we must create a loop. Otherwise, Faraday law wouldn't be applicable, right? So there must be some loop, conducting loop. So let's create this. Let me put sort of like a rod, conducting rod, and it's not just a straight piece of wire. It has this shape. Right, so let me draw it like this. So this is the center, and then over here, this shape, conducting rod. And this point is right in front of this point, dash line. And this angle between this line and this part of the rod, it's alpha. And this angle is also alpha over here. Right. Again, classical U-shaped rail, just a straight piece of wire over here, just a rod, straight rod, but I bend it like this. And this rod is moved this way with velocity, where is velocity? 5 meters per second. And something else, let me check what else needs to be mentioned. I need to give you, no, it looks like, the angle, I gave the angle 20 degrees. Okay, why not? Alpha, let's say this and this angle, 20 degrees. Just for fun, I give you a number actually. Right. So we need to answer the question, are we going to, since we have a magnetic field, right? External magnetic field, there is a loop, conducting loop. So of course we have all ingredients to apply Faraday's law and see, are we going to induce EMF and are we going to induce current in this loop? Right. So we just need to answer this question, right? And you know what, before I start solving problem, let's assume that we're not discussing that stretch of time or moments of time when this conducting rod crossing this line. So pretty much we assume that when this rod is over here, we're not discussing this moment of time. Pretty much we started discussing when the rod is over here, right? But the moment when this rod crossing this line, we're not discussing, because that will be a little bit more complicated. That will be more complicated. Okay, so that's the situation. And we will apply Faraday's law. And of course, you remember, when we apply Faraday's law, we divided application into 2 steps. First, we can apply Lenz's rule in order to find a direction of the induced current. And then we will drop that minus and find the absolute value of EMF and then actually the value of the current. So let's do the same. Let's divide into 2 steps. So let's first find a direction. I induced direction. And actually it's time to erase this part, since I'm getting closer. I have a bunch of markers here after a year and a half of teaching here. So, in order to apply Lenz's rule, of course, first we need to get to this point. We need to figure out what happens to the magnetic flux. Is it growing in time or is it dying in time? And of course, flux is BA. So 3 parameters again, B, A, and the angle. So let's do it. B, of course, external area of the loop and the angle. Right. So magnetic field, external magnetic field, of course, it's constant, it's uniform, right? So, and of course, we assume that there is no end. So basically, this magnetic field extends all the way to infinity. So this rod is not going to reach the end of the magnetic field. So magnetic field is constant. So it doesn't change magnetic flux. Then angle, okay? Again, it will be constant. It's either 0 or pi. So let me pick area vector this way in the direction of the external magnetic field. So as a result, angle is 0, but anyway, it's constant. Right, 0 degrees, but anyway, it's constant. Right. But what about the story with the area? Area of this loop, of course, changes because we move this rod further and farther and farther away. Of course, this area is growing, getting larger and larger, this area of this loop, right? So area is growing. Changes in time, it's growing, right? So as a result, if you multiply them, B, A, and cosine of this angle, flux is growing in time, of course, right? So of course, flux is growing. So we're getting to this situation. If magnetic flux is growing, so of course the loop, response of the loop will be, it will start driving induced current in such a direction so that the induced magnetic field will be in the opposite direction to the external magnetic field, trying to suppress growing flux. So in this case system, the loop rebels, behaves like a rebel, like Che Guevara, right? So I can write it rebels, right? So, and of course, B induced will be in the opposite direction to B external. Right? So it means that within the loop, I can draw a bunch of induced magnetic field lines, opposite direction. So this is dots. So this will be crosses. So that's B induced, right? Let me check if I got the same direction. Yeah, the same direction. Okay, so and now right-hand rule. There is the loop, right? So induced magnetic field into the board, right? Into the board, like this. Wait, no. So in order to get that direction, I need to curl my fingers like this. You see? Now, direction of the magnetic field and direction of my fingers are the same, right? And then direction of the thumb gives me direction of the current. So which is this way? Clockwise direction. Right, so this will be I induced here, here, here. So I induced clockwise direction. So over here I can write right-hand rule number 2. So I induced CW. So direction of the induced current. So and now we need to find its value. So part B, we just need to, now we don't need that minus, we just need to look at the absolute value of EMF. So part A, now part B. So EMF equals to absolute value of d phi over dt. So magnetic flux, it's a BA cosine of angle. So let me write explicitly. Okay, minus, of course, I will drop because I already put signs of an absolute value. So d over dt, it's a B external times A and times of cosine of 0 degrees because we already pick direction of the area vector towards you, right? So the angle is 0 degrees. So that's why I wrote it over here, cosine of 0 degrees. Cosine of 0 degrees is 1, right? So we have B external times A. External magnetic field, constant. It doesn't change in time. So it means that this B external can be taken outside of the sign of differentiation. And actually we can be taking outside of the sign of absolute value because now this is just a magnitude. Magnitude of the magnetic field. Wait. So that B external can be taken outside of the sign of differentiation and the sign of an absolute value. Right, so I can write it as B external times the absolute value of dA over dt. Right. And now we have to be careful with A. A consists of two parts. A, it's this whole figure. Right? So now let me write underneath. So this area A consists of two parts. Let me label some points. So this point, you know what? I'm running out of colors, right? Probably I will use black. Yeah, I don't have enough black over there. So which way I label it? All right, P point, then K, then what point? R, F, M. This point will be R, this point F, and this point M. So let me label these points like this. P, K, R, F, M. So this area, it's the area of the whole thing. So it's an area of P, K, right, R, F, M, right? Lots of subscripts, right? So, and of course, how can we find that area? Of course, that area consists of two parts, right? So I can at least, I want to divide it into two parts. First part, P, K, R, M, this rectangle, and the area of this triangle. I want to write it like this. So it is equal to the area of PKRM rectangle plus area of this triangle RFM plus area of RFM, right? Okay, so now let me plug it. So B external and absolute value of d over dt of these triangles PKRM plus area of RFM. Okay, my marker is getting to losing contrast. I think here I prepared a new one in advance because I was afraid of that. Okay, now look carefully. What can you say about the area of this triangle in time? As we drag this rod, this rod, this rod, bent rod, that way, what happens to this area in time of the triangle? Nothing. Nothing. The area of this rectangle, right, it's growing because this point R and M, they are moving this way. So the area of this rectangle increases in time, but the area of the triangle stays the same. So if this area stays the same, if you differentiate it with time, it's 0. It gives you 0, nothing, right? So now let me show you this. This area is, wait, this new marker, it takes some time before it starts working properly. I forgot. So this is constant. Okay, maybe I will just apply more force. Constant in time, right? Constant in time, right? So as a result, this derivative gives you out of that 0, right? So this will be 0 when you apply d over dt. Or maybe I will write here in the brackets d a r f m over dt equals to 0. Right? Okay, so as a result, pretty much the problem is reduced to the classical problem, when the rod is just a straight rod, because this triangle basically doesn't contribute anything. So yeah, I increase complexity, but from the physical point of view and mathematical point of view, that complexity, geometrical complexity, did not increase complexity of the problem. Effectively, it's like a problem when you have just a straight rod which is moved that way, right? Because contribution from that triangle gives you nothing, right? But of course, it needs to be justified why the triangle doesn't give you anything. Okay, so now let me continue this finally. B external n times rate of change of this triangle. Oh, not a rectangle. A, B, K, R, M. Right. So at this point, classical idea. So how can we move from this aerial velocity? Pretty much it shows us how fast area changes in time. So how can we move from this aerial velocity to just linear velocity, which is given in the problem? In order to make this transition, we need to use the trick which we discussed in the recitation classes. Let's introduce temporarily, just for a very short period of time, this distance. Let's introduce this distance where I can introduce it here, maybe. Let's introduce this distance, x. So let's introduce this distance x. And once you do that, this area can be easily written L times x. Again, like we've done in our recitation classes several times. So let me open my explanation box and write introduce x. And as a result, this area equals to L times x. Right? Okay, so as a result, we're getting B external and d over dt L times x. L is constant, can be taken outside. L is this width. L times x, area of this rectangle. So it will be B external times L and times absolute value of dx over dt. Right? You remember that this trick with introducing x in our recitation classes, we discussed that. So in dx over dt, how fast this distance changes in time. Of course, that's velocity. That's the velocity of the rod. So this is just the velocity of the rod. Velocity of the rod. Okay, so the final push. So it will be. Okay, I guess I will have to use that part of the board. So B external times L times V. So everything is given. You can plug, multiply, calculate. I will look at my notes. It is 0.3 volts. 0.3 volts. Right. And the final step, let's assume that at this particular moment of time, resistance is given. Right? So when the rod is at this distance from that edge, so let's assume that the resistance is given, and the value of that resistance is 0.1 ohm. You know what? Okay, I think I will be able to fit it over here. So I induced equals to, you know what? Let me write over here. So let's assume resistance. This marker 0.1 ohm, right? I think I said, yeah, right, 0.1 ohm. So let's assume at this particular moment of time, because resistance is a function of time, because you can move this rod farther and farther away. Of course, more conductor is involved. Of course, the resistance slowly growing, but let's assume at this particular moment of time, resistance is given. So it will be 0.3 volts divided by 0.1 ohms. So it will be 3 amps. 3 amps current, right? Right? Yeah. So that's the problem. Again, I sort of added complexity by adding this triangle, but it's a pure geometrical complexity. But from the point of view of physics, I didn't make this problem more complicated. Except for, of course, you need to here add this area of a triangle. And so, okay, guys, you see angle, that area is constant. And if you differentiate it with time, of course, it gives you 0. So it doesn't contribute anything to the induced EMF and induced value of the current. So that's how we used Faraday's law. That's how we used Faraday's law. Enough of that. There's another problem, but you can read it by yourself. It will be in my notes. Okay, so next, after we introduced Faraday's law, we started discussing inductance, right? Because in order to describe the work of inductors, you need to know Faraday's law. Faraday's law is behind the work of inductors, right? So now let me discuss. We're not going to calculate inductance. Usually, let's discuss direction of the induced current and the potential difference across inductors. Conceptually, of course. And then this problem will be really trivial. Okay, Can I start erasing? Or should I wait for a sec? Seven, and it's a conceptual discussion. Actually, I will combine conceptual with the problem in the same. So potential difference produced by the inductor. Let's discuss. Right, delta V produced by an inductor. And of course, inductance we denote it using L capital, inductance. Units, Henry, right? You remember Henry. Units of flux, Weber. Units of inductance, Henry, H capital. And so, first I just want to state this Lenz's rule for the case of an inductor. You remember at the very beginning of this exam review session, I told you that behind the work of an inductor, Faraday's law. Faraday's law is behind the work of an inductor, right? So, and of course, Lenz's rule also. Lenz's rule, right? But of course, since the system is slightly more complicated, it's not just one loop. We have basically thousands of loops, right? Stuck next to each other, right? Of course, it's easier, more convenient to adjust Lenz's rule slightly, and it's stated in a slightly different way. So when we discussed a loop, we talked about magnetic flux all the time. But when you discuss the work of an inductor and potential difference across an inductor, it's better to talk about the current. Loop didn't like when flux was changing. Inductor doesn't like when original current which goes through the inductor, it doesn't like when current changes. If current is constant, di over dt is 0 and delta V will be 0. So in this case, inductor is not going to produce any potential difference and is not going to across itself. And as a result, it is not going to produce any induced current. So let me state it, and then we will start changing current and discuss what happens in this case. So let me write this. So inductor L does not like changes. Okay, my marker starts working slightly better. It takes a little bit of efforts and then it works fine. Doesn't like changes. Okay, let me write it the way I wrote in my notes. Doesn't like when current changes. Let me write current changes. Doesn't like when original current. I usually use subscript 0. Original current when I not changes. So as a result, it responds in a different way. So let me state these three situations. So let's assume that we have maybe slightly smaller. So let's say here is our inductor, right? L, yeah, let me write underneath L, right? And the original current flows this way. So that's I naught, this current I naught, right? Which is maybe produced over here, maybe there is a battery, right? Or maybe complicated circuit. And then this original current flows through the inductor. If that current is constant, inductor doesn't do anything. It's happy, right? So okay, let me write this way. Underneath, I naught is constant. So if I naught is constant, then inductor doesn't do anything. Then L does not produce delta V. And again, which delta V? Over here, you see? It's the potential difference between the electric potential at the final point and initial point, right? So as a result, delta V will be 0. Again, maybe I should say this is our final point, right? Final point, and that is our initial point. Yeah. Initial because that's where original current enters the solenoid, and this is final because that's where current exits the solenoid. Initial and final. So delta V will be 0. Doesn't produce delta V. So delta V, which is V final minus V initial, equals to 0. So solenoid doesn't do anything. Now, second situation. Yeah, let me also write. So I induced will be 0. I induced will be 0. But if current changes, let me draw basically the same picture, but now for the second situation. So that's our inductor, right? L. And now let's assume that this original current changes in time. So that's I naught. And now let's assume it increases. Changes in time. Changes in time. And of course, in this case, solenoid wakes up and starts doing something. What does it do? It wants to keep this current as constant as possible. So if current increases, so the inductor starts rebelling. It will start driving induced current. Of course, first it will produce potential difference, proper potential difference, so that the induced current will flow in the direction opposite to the direction of the original current. Opposite. So it means that induced current will flow this way through the rest of the circuit. Opposite direction. So you see here current is sort of up, here down, here again it's a down, and this induced current is up. So I induced through the rest of the circuit. Okay, let me write it down. So since I naught is increases, right? So then I induced is in the opposite direction to the original current. Basically, you see similar logic, but here loop didn't like when flux through the loop was changing, and it's either it was rebelling or it was supporting. Now it's all about current. If current constant, nothing happens. If current starts increasing, the inductor will wakes up and start driving current in the opposite direction, trying to suppress growing current. All right. So now, and the next step. So what can we say about the electric potential at the final point and initial point? So that is our final point, that is initial point. And now think this way. In order to produce current, induced current with that direction, think of this inductor as some small, effectively small battery. Think of this as some kind of small battery, right? And of course, the polarity will be, you know what, I don't like that. Let me separate them a little bit like this. So, and the polarity must be here plus, here minus. You see? Plus, minus. In that case, of course, current flows from plus to that minus through the rest of the circuit. So it means that this point, initial point, is at higher electric potential. Final point, this final point is at lower electric potential, right? So here we have basically minus, here we have plus. So it means that V, which I wrote in my notes, V initial is larger than V final. Three simple steps. What happens to the current? If it's growing, the induced current will be opposite to the direction of the original current. And once you know the direction of the induced current, think about the polarity of this kind of fictitious battery. Think of the polarity of this fictitious battery. So here must be plus, here must be minus. So it means that initial point is at higher electric potential than the initial point. So that's how it should be done. It should be analyzed, and that's what I asked you to do in the last quiz number 7, right? The third part. So, and now let's discuss the last situation. So here current was constant, now it was increasing, and now let's assume that it's decreasing. So the inductor, right? So original current I naught, let's say, decreases, right? And so now again, inductor doesn't like when current changes, but now current is dying. So of course, now inductor tries to support it. It will produce the proper potential difference across itself so that induced current will flow in the same direction as the original current. So original current flows this way. So and of course, induced current also flows this way. So that's I induced. In the same direction, you see current up, current up. Right. And again, think about the some fictitious battery. So solenoid starts working basically like small fictitious battery. With which polarity? In order to get this direction, of course, here there must be plus, here there will be minus, right? So with this polarity. So it means that our final point, this is our final point, right? So this is our initial point. So the final point is at higher potential than initial point. Right? So now let me write it down. So if I naught is dying, then of course I induced will be in the same direction as I original. And once you know direction of the induced current, think about this fictitious battery and the polarity. So as a result, V final is larger than V initial. V final is larger than the electric potential at the initial point. So that's Lenz's rule adjusted, restated for the case of an inductor, because it's just easier, faster to apply this rule to analyze behavior or work of an inductor. Right? Quite often I give among multiple choice questions a question about this, and lots of troubles. Usually lots of troubles, right? And almost like a 50-50. Although it's almost like not almost, yeah. As I said, Lenz's rule restated for the for an inductor. Okay, so now let's quickly solve the problem. It's not it's as simple as these conceptual discussions. Yeah, the problem. And this marker it's fresh, it's difficult to erase. I guess I have to clean the whiteboard. Okay, I'll finish this problem and then I will clean the whiteboard. You know what, let me clean it now. Short break. So the problem. Yeah, it's a 7, so that was our basically part A, and now let's say this is part B. So we have a coil. No, this is inductor. So we have L inductor equals 280 milli H Henry. You remember units of inductance, L. Then current changes through this inductor. So original current, let's say I initial sub I sub I, initial current is 25 amps, and then it changes to I final, which is 10 amps. So current is going down, and let's assume current is going down linearly, right? So it changes linearly, and this transformation of currents happens over the period of time of 360 milliseconds. So delta T, 360 milliseconds. And let me write over here, changes linearly. current changes linearly, basically along a straight line in time. It's a very important statement, otherwise we wouldn't be able to solve the problem. Right? So let me draw the picture and then we will start discussing, start solving. So let's say this is our inductor, and here's a battery which drives the original current through this inductor. So that is L. And original current, I use green. Okay, let me use also green. So I naught. And this original current changes. It's going down, right? You see, it's going down. And of course, as a result, the inductor will respond. Actually, we can discuss first conceptually. So this is our final point. That is our initial point. Again, according to the direction of the original current, that is our final point. That is our initial point, right? And conceptually, current is going down. It's this case. Of course, this inductor doesn't like that fact. Of course, it will start producing potential difference across itself. Basically, it's a production of the inductor. So with such a potential difference, so that the induced current will flow in the same direction as the original current. So it means that induced current will flow this way. So that is I induced. And in order to get this current, again, think about some small fictitious battery. So solenoid starts working because inside it has some amount of energy. So it means that it starts working effectively as a small fictitious battery with this polarity, plus over here, minus over there, so that the current will flow from plus, so the rest of the circuit, to the minus. So it means that final point is at higher potential. So over here we have plus, and initial point is at minus. Okay, minus, it means just lower potential, right? So it means that over here, all right, so I can write that V final is larger than V initial, or delta V is positive. Okay, so that's conceptually what we just discussed, and now let's just solve it. Let's just solve it. And solution is quite simple. The formula is here. Again, delta V across the solenoid, across an inductor, minus L di over dt. Right? So that's conceptually. Let me write it over here. It's a conceptual analysis. Okay, conceptually. And now let's calculate. So it's a part A and B. We already have B. Okay, so now let's calculate. Calculate delta V. So that was conceptually. Now calculate. So delta V equals to minus L di over dt. I just rewrote this formula again, which we derived in the lecture. Okay, so since current changes linearly, of course, this di over dt can be changed with delta I over delta t. Right. So again, we discussed that many times in our recitation classes. Delta I over delta t. And so final value of the current we know, initial we know. So we just need to plug it and that's it. So minus the value of L, 0.28 Henry, 280 millihenry. So it's a 0.28 Henry. And currents, final 10 amps minus 25 amps, and divided by the stretch of time, milliseconds, so it's a 0.36 seconds. 0.36 seconds. Okay, so if you calculate it, and the answer is going to be positive. We have minus in front and minus from here because this will give you minus 15. So minus and minus, it will be plus. And let me look at the numbers. So plus 12 volts. So now we got number and the sign. Here conceptually we just ended up with the value, with the sign of the delta V. So delta V is positive. So it means that final point is at larger potential or higher potential than the initial point. So that's what I was planning to discuss about inductors. And again, the major issues over here, answering it conceptually. So there's another problem about inductor, but okay, so now it's time to move into waves, right? So we finished this box, traveling wave, electromagnetic wave, basically potato potato. So let's just discuss electromagnetic wave, right? And then interference. So we have electromagnetic wave. This problem 8, problem number 8. So EM wave, electromagnetic wave. And frequency is given, F, just a normal frequency, 60 Hertz. Very low frequency for electromagnetic wave. Of course, as a result, wavelength is going to be gigantic. But for me, just to discuss calculations, discuss physics, right? All right. Practical part of the problem is different. So we have this electromagnetic wave which propagates in the positive z direction. Right. Then electric field oscillates in the x direction. Right. And amplitude of the electric field is given. You know what? Let me first draw the picture. Draw electromagnetic picture of electromagnetic wave, and then I will start writing. What needs to be found. Right. So let me draw the picture first. Right. So it propagates in the z direction. Right. So it means that this will be my z direction. Then electric field oscillates in the x direction. So let me position x this way. So that's our x. And then, of course, what's left? This is left for the y direction. And it's still a right-handed coordinate system, because if you take a cross product of x times x and y, so you will get z direction. So it's a right-handed coordinate system. It's fine. Right? So propagates, electromagnetic field propagates in the z direction, and the electric field oscillates in the x direction. So I can draw electric field traveling wave. Electric part. Right, so that will be my electric field. Right, so E. And amplitude is given, so let me show it. So that's amplitude, so E naught equals to, what's the value? 2 volts per meter. 2 volts per meters. Then, of course, if this is electromagnetic wave, of course, there must be magnetic field oscillating in phase, in unison. But of course, now it should oscillate in the y direction, because there is only one direction left unused. It propagates in a z direction. Wave propagates in the z direction, right? This oscillates in the x direction, and you remember these 3 directions, E, B, and V, must be perpendicular to each other, mutually perpendicular. So it means that magnetic field must oscillate in this direction. Right, so this will be magnetic field. And still propagates in the z direction together with the electric field. So that's our B. Magnetic field amplitude for now is not given, but we will have to find it. Okay, so that's the situation. And now let me write expression for the electric field in this form for this particular situation. Right? So electric field equals E naught times sine of K. Which symbol do I have to use here? You remember over here we had kx, yx, because electromagnetic wave in this situation propagated along x direction. In our case, it propagates along z direction. So it means that this x must be changed with z. If our wave propagated along the y direction, we would have to write over here y. But here in our problem, we have to write z. Be careful. That's where first place for lots of mistakes. So kz. Then minus or plus. Actually, plus is when wave propagates in the negative, in this case, negative x direction. But since electromagnetic wave propagates in the positive x direction, so there must be minus. You remember that change in the signs. If there is a minus, it means positive direction. Positive x or positive y or positive z, right? So since electromagnetic wave propagates in the positive z direction, of course, I have to put here minus omega t, and of course I can write additional phase, initial phase, but let's assume most of the time when people talk about electromagnetic wave, quite often they are not interested in the initial phase, like I used a lot in my optical systems, right? Detecting electromagnetic wave produced by the laser, and most of the time I'm not interested in the initial phases, right? So let's just assume initial phase is zero. But one part I left not filled on purpose. Which subscript do I have to use here? Pretty much I'm just trying to write something like this. This subscript tells us along which axis electric field oscillates. And the electric field oscillates in the x direction. So here we must put x. That's the second place for tons of mistakes. Pretty much here and there. That's most of the two places where there are most of the mistakes if I give a problem to analyze electromagnetic wave and write mathematical expression for the electric field and the magnetic field of the electromagnetic wave. So here, x, it's a axis along which electric field oscillates. E sub x equals, so that's in general, but still we need to find wave number, angular velocity, angular frequency, and then we will have to write similar things for the magnetic field, right? So I can erase now this. So effectively at the end, I want to write mathematical expression for the electric field and mathematical expression for the magnetic field of this electromagnetic wave, So k, so we need to find k. K by definition is what? It's a wave number, spatial frequency basically. Spatial frequency. It's a 2 pi divided by spatial periodicity. Right? So we need to find lambda in order to find k. Can we find lambda? Frequency is given. And we know how we can make a transition from a frequency to the wave number, right? I mean, to the wavelengths, using the speed of light, speed of the wave, because we know this is electromagnetic wave and it travels with the speed of light. So V equals to lambda times F, right? Okay. So K equals 2 pi over lambda. So I will write so. We need lambda. And lambda can be found. C equals lambda times F. F is given. Lambda we need to find. C, speed of light. Right? Okay, so now let's calculate. So it will be C over F. C, it's a 3 times 10 to the power of 8 meters per second speed of light. Right? And another situation, sometimes I give a problem on the exam, electromagnetic wave is given, and student they feel like they need to know the speed of the wave, and they're sitting without realizing that if it's an electromagnetic wave, it travels with the speed of light. You need to connect that, right? So, and sometimes I would walk around several times trying to give them some hints, right? So come on, you know that it's a speed of light, right? So frequency 60 Hertz. Wow, it's a very low frequency. Of course, as a result, wavelength is going to be gigantic, right? So I will look at my notes. It will be 5 times 10 to the power of 6 meters. Sorry, I should have changed, right? Just basically now I recall this problem. It's not a problem. It's not everything is correct. It just wavelength is gigantic. So, and now, yeah, we can find the wave number. So, K equals to 2 pi divided by lambda. And in which form I left it? So it will be 1.26 times 10 to the power of minus 6 inverse meters. Yeah, that's the wave number. So we found this K in order to write down the expression. Again, amplitude is given. We found this. Now we just need to find omega, and that's it, because z and t are variables. So now we need to find angular frequency omega. And of course, by definition, angular frequency is a 2 pi over t. Omega is 2 pi over temporal periodicity, temporal periodicity. Period and the frequency are connected. They are reciprocal to each other, right? So we can write it as 2 pi f, right? So it's 2 pi times 60 hertz. It will be, in which form I left it? Actually, I calculated. 2 pi times 60 hertz. So it will be 377 radians per second. So angular frequency. So now we have this, and we are ready to write down expression for the mathematical expression for the electric field. Right? So now, and you know what? I will write together mathematical expression for the electric field and the magnetic field at the very end. So now, pretty much we are ready to write down E. But we also need to write similar expression for the magnetic field. And in order to do that, we need to know magnetic field amplitude. Again, quite often, students don't remember, they forget about the relationship between amplitudes of the electric field and magnetic field in the electromagnetic wave. And as a result, quite often they just grab amplitude of the electric field and use it as an amplitude of the magnetic field. Of course, it doesn't look good. So we can find B naught. So it will be E sub 0 divided by C. E sub 0, 2 volts per meter, divided by 3 times 10 to the power of 6. 8. Sorry. 8 meters per second. Again, I will look at my notes. 6.67 times 10 to the power of minus 8. Oh, minus 9. Yeah, units of Tesla. Okay, so now we're all set. So now let's just start writing mathematical expression for the electric field and mathematical expression for the magnetic field. So E, it's almost ready, right? So it will be E sub x function of z and t. Then amplitude, so 2 volts per meter times sine k, this 1.26 times 10 to the power of minus 6 inverse meters times z, right? And minus omega t minus, where is omega? This 377 times t, right? Okay, so mathematical expression for the electric field of this electromagnetic wave. And now let's write down expression for the magnetic field, B. And immediately, it's a function of z and t, the same. But which subscript do we have to use? Careful, again, that's where tons of mistakes. Magnetic field oscillates in the y direction. So it must be shown, and you need to show the subscript y, b sub y. Then, of course, amplitude of the magnetic field, this is 9, right? Okay. So equals 6.67 times 10 to the power of minus 9 Tesla. And then the rest, this sign, all this construction is exactly the same for the electric field and the magnetic field. You see over here, exactly the same. So you just need to rewrite it. And you know what, since I'm afraid that I will not be able to fit it. I will just write kx minus omega t. Kz. Kz minus omega t. Right. And let me emphasize that this part, so effectively exactly the same, right? Z and time dependence exactly the same, because you see they oscillate in phase, in unison, right? Electric field and magnetic field. So that's electromagnetic wave. Again, most of the time students have no troubles with finding k's and omegas and lambdas and frequencies and so on. But when it comes to writing the whole expression, subscripts, and direction of propagation, that's where most of the time, most of the mistakes. Next, let's discuss interference. So interference, then double slit, diffraction, grating, ray optics. Oh, we still have quite a few problems. So, two out-of-phase radio antennas. Okay, interference, this part. Right. So let me write that down. We have two out-of-phase radio antennas. And the frequency, I think, is given. Yeah. So frequency 300 megahertz. And you know what? Let me draw the picture. So this will be my first antenna. This will be my second antenna, right? So let's call it antenna number 1. You know what? Let me use different colors. So that will be black and this will be blue. So antenna number 2. So effectively what happens? Yeah, and we assume, of course, that these two antennas produces basically identical circular waves. Of course, circular, I'm talking about circular because I'm looking at the cross section, right? But of course, in life, of course, they are spherical waves. Identical, it means the same amplitude, the same frequency, right? And what else? And the same wavelengths. So pretty much they behave in exactly the same in the same way in space and time. So this antenna produces its own wave. These are just wave fronts. You remember wave fronts, collection of crests, between them troughs, again crest, troughs, and so on, basically. And then this antenna produces its own waves, right? And of course, they are going to overlap, interfering, right? So, and for example, if here it's a point of constructive interference, if you move next, it will be destructive, then constructive, destructive, constructive. And of course, between those two, between points of constructive and destructive interference, there will be something in between, right? So pretty much we can analyze any point. So, but the problem asks about this particular point. Let's say this point, right? And the distance to that point from this second antenna is R2, 5 meters. And distance from this antenna to that point, R1 is 2 meters. So we need to analyze this point, right? I don't know, maybe there's a person there holding an antenna, right? Is he going to detect maximum signal with doubled amplitude, or nothing, or maybe something in between? So we just need to answer the question. So at this point, is it constructive or destructive interference? Okay, so we spent quite some time deriving these conditions. So pretty much now all these problems are only about applying this condition. So let me just rewrite this condition over here. 2 pi over lambda times delta r. path length difference plus the inherent phase difference. And then we just need to calculate. So if it will be equal to integer number of 2 pi is constructive, if that will be equal to m plus 1 over 2 times 2 pi, then it will be destructive interference. Right. So we need to find, let's answer the question about inherent phase difference, then delta R, and then wavelength. Inherent phase difference, that's, I don't know, 75% of students messing up usually at this part. Inherent phase difference. And as I told you in the, we discussed this in the recitation classes. So this information pretty much is hidden in, most of the time, is hidden in the words of, in the statement of the problem. If the problem says that there are two, for example, in-phase speakers or in-phase antennas, it means what? If they are in phase, it means that the inherent phase difference is 0. If the problem says you have two out-of-phase speakers or two out-of-phase radio antennas like what we have in our case, so the key word over here, out of phase, pretty much that's how the researcher or engineer who sets up this situation wants to tell you guys that over here, that initial phase, basically you can easily change the phase of the wave, right? Just the function generator, you can easily control the phase, right? So it means that initial phase of this wave, let's say pi, initial phase of this wave is 0. Of course, as a result, inherent phase difference is pi, out of phase. Instead of telling you the initial phase of this wave and that wave, they can say out of phase radio antennas. Pretty much that information is hidden in the statement of the problem. Out of phase, it means this is pi. So it's usually the easiest part, but I don't know, 75% of students create mistakes at this point. So pi, basically because out of phase. If in phase, then 0. Usually, most of the time, students just assume 0, but it doesn't have to be. So now, inherent the path length difference, delta R. In this case, a simplified geometry, I gave you immediately R2 and R1. So path length difference is just the distance between R2 and R1. It's just that additional distance that, for example, the second wave has to cover relative to the first wave on the way to the point in question. So R2 minus R1. So it will be, of course, 3 meters. The path length difference is 3 meters. Additional distance. Now, we found this, now wavelengths. And of course, wavelengths can be easily found because we have radio antennas, radio waves, electromagnetic waves. They all travel with the speed of light. Radio waves, microwaves, terahertz, right? Then far infrared, near infrared, visible, ultraviolet, X-rays, gamma rays, all electromagnetic waves. They all travels with the speed of light. So as a result, we can use this one. V equals lambda times f. Frequency is given, speed c, speed of light, and so we can find wavelengths. So c over f, 3 times 10 to the power of 8 meters per second divided by 300 megahertz. Mega 10 to the power of 6, right? So it's 10 to the power of 6, plus there are 2 zeros in front, so it will be 10 to the power of 8. So it will be 3 times 10 to the power of 8 hertz, which is 1 over seconds. So the wavelength is just 1 meters. On purpose, I picked the easiest numbers. Right. Okay, so the wavelength is 1 meter. Basically, it's a distance between these two wavefronts. Right. Okay, so now we have everything, so we just need to plug them into this condition, right? And get to the come to the conclusion. So 2 pi over lambda. Lambda is 1 meter. I'm just applying it over here, right? So times delta R, 3 meters, plus inherent phase difference, pi. Okay, so 6 pi plus pi, 7 pi. And at this point, guys, be careful. At least in the recitation classes, I observe it quite often. This. Okay, let me get some water and then we'll continue. So, quite often when students get to this point, after spending some time getting through this solution, they feel so excited. Okay, it's almost done, right? And they try to jump to the conclusion too fast. They see it's kind of simple expressions, just 7 pi, and immediately they think, okay, this is also simple. And immediately write, okay, constructive interference. Don't make this mistake. Slow down and look carefully. We have odd number of pi's. Odd number, 7, odd number, right? But here you have what? Integer. Okay, m, you remember m, it's a 0, 1, 2, 3, and so on. Just an integer. So integer times 2. If you take any integer and multiply it by 2, you will get even number. Even number. Here, even number of pi's. Here you have odd numbers of pi. It's impossible to get from this condition odd number of pi's. It's actually destructive interference. We need to look carefully, right? So be careful at this point. I observed that lots of, okay, not lots of, but some number of students make here a silly mistake because they start rushing to the conclusion. So m plus 1 over 2 times 2 pi. Definitely not constructive, so let's discuss destructive interference. Which m is going to give us 7 pi? 0 not, because it will give us pi. 1, 2 over 2, 3 over 2, 3 pi. No. 2, 4 over 2, 1 over 2, 5 over 2. It will give us 5 pi. 3, it's 6 over 2 plus 1 over 2, 7 over 2 times 2 pi, 7 pi. So that's m equals to 3. So that's the point of constructive interference, which corresponds to the integer m equals 3. Somewhere nearby there will be a destructive interference, sorry. Point of destructive interference corresponding to integer m equals 3. Somewhere nearby there will be destructive interference corresponding to m equals 2, then m equals 4, and so on. Right? So destructive interference. So that guy with the antenna is not going to detect anything. Pretty much in his antenna he will observe only just a noise, no signal. But if he steps away, for example, some, I don't know, maybe a meter or so in some direction, right? So he will be able to spot the point of constructive interference, and he will be able to get the strongest signal, right? So, not complicated, I would say, problems of this type, except for inherent phase difference. Lots of troubles. Enough of this. You know what, conceptually, let's just quickly discuss conceptually one question. We discussed that in one of our recitation classes. So let me put like a small bullet. Right. So what if we have two, okay, this problem is solved, right? Now, two interference of two circular waves. So let's say we have a source of the first wave, and I'm drawing wave fronts, right? Okay, I'm doing my best, but they're still distorted. So these are wave fronts. Then let's say there is a second source over here of circular waves. Second source, and let's say, of course, with the same wavelengths, the same period, and the same amplitude. Because that's where, for those conditions we derived this condition, right? So then wavefront second one, then the third one, and then the fourth one. So these are wavefronts. So it means that here we have a crest, then trough, crest, trough, crest, trough, and so on. And for the black one, exactly the same story. So crest, trough, crest, trough, crest, trough, and so on. So they interfere. So, and now we need to discuss a few points. So what if we pick, for example, this point? All right, point A. Are we observing constructive or destructive interference? Will we observe constructive or destructive interference at that point? Analysis is very simple. What do we have? We have a wavefront, blue wavefront going through that point. Then we have black wavefront going through that point also. So wavefront, it's a collection of crests. So it means that at that point we have overlapping of what? Crest over crest. Crest over crest, constructive interference. So amplitude will be doubled. So over here we're going to have amplitude will be doubled, amplitude of the resultant wave. So over here we're going to have constructive interference, C, constructive interference at point A. Then let's take this point. For example, this point, point B. So that point is between two wavefronts, black wavefronts. So it means that that point is in the black trough between wavefronts. This is crest, this is crest. So this point is in the black trough, right? But at the same time, it's between wavefronts, blue wavefronts. So it means that it's also in the blue trough. So if you have black trough and blue trough on top of each other, again, it's a constructive interference, right? So trough over trough is as good as crest over crest, crest over crest, and trough over trough. So constructive interference. So at this point, again, we still have constructive interference. And so now let's take point, for example, which one? Let's take this point. That was A, B. Let's call it point D. Oh no, D is that's we label constructive or destructive. Let's say point, I know, Q. So now let's analyze that point again in terms of where that point relative to wavefronts, relative to crests and troughs. So it is on the black wavefront. So it means black crest. Then it is between blue wavefronts. So it means it is in the blue trough. So if you have black crest and blue trough, of course, they are going to kill each other. They're going to cancel each other completely. Of course, at that point, the amplitude of the resultant wave will be zero. Destructive interference, destructive interference. So at this point, we're going to see, let me draw it here, destructive interference. So constructive crest over crest, constructive trough over trough, and of course destructive because you have crest over trough. So very, very simple analysis, right? Another situation, again, you will see in my notes when I send it to you. If you, for example, let these circular waves propagate all the way to infinity, very, very far away, pretty much at those points, you're not going to see the curvature of these circles. For you, basically, these wavefronts are going to look like a straight lines. But still, the same analysis can be applied for those wavefronts, right? Again, if it's a crest over crest, constructive, line over line. If it's a trough over trough, still constructive, right? Whew. So that's interference. Now, you know what? I will skip double slit, or maybe I will discuss. Let me just put it on, put it aside. All right. So pretty much now we discussed this. We discussed that. Now it's time to discuss diffraction grating, double slit. All right. Then ray optics and lenses. So what about time? So 7:40. So 7. All right. So 3 hours, 10 minutes, right? No, actually it's still nice. As I said, usually the final exam review session takes about more than 4 hours, right? 4.5 most of the time, because more material. Okay, so now let's discuss, you know what, this problem will be too complicated. Oh, we'll see. So, diffraction grating. You know what, let me draw immediately the picture, and then I will start writing down what is given. So pretty much we have a diffraction grating. All right, this screen is given, so some distance to the screen is given, and then this diffraction grating is illuminated by two lasers. The wavelength of the first one is known. It's some red laser, so the wavelength is known. And then you can observe bright and dark spots on the screen. And then there is a laser which of an unknown wavelength. And also you will observe interference fringes of that unknown, created by that unknown light. So we just need to find the frequency of an unknown light. I'm sort of trying to use grating as a spectrometer, effectively, right? Effectively as a spectrometer. So now let me draw the picture. So that's my diffraction grating, right? With thousands of slits. Distance between those slits about a few micrometers. And as I said, it is illuminated with two lasers. The first one, the red one. So let me write it over here, lambda r. R stands for red. You see subscript r, lambda subscript r. 632.8 nanometers. Oh my God. 632.8 nanometers. Yeah, it's somewhat reddish light. That's ugly. Nanometers. Let me rewrite it. Nanometers. Then there is a laser of an unknown wavelength. So let me use blue color. So lambda x, and that's what we need to find eventually. And then, of course, there is a screen, and we observe interference pattern produced by these two lasers, right? Is the wavelength, is the length given, distance to the, no, it's not given, distance to the screen is not given. Then this is the center of the whole system, right? And let me draw this interference, bright and dark spots. At the center, all the time, there must be a bright spot. It doesn't matter which laser of which wavelengths you use. Bright spot at the center. So let me first draw a red one. So this will be the bright spot produced by the red one. Of course, it corresponds to m equals 0. And then let me draw, this will be red corresponding m equals 1, give or take. Then there will be over here m equals 2, so that is m equals 1. That is for m equals 2, m equals 1, and over here m equals 2. So these are bright spots produced by a red light. Wavelength is known. Now blue, of unknown. Right. So of course, again, it will be at the center, so m equals 0. And then the blue guys position somewhat closer. So that is m equals 1, m equals 1, and this over here, m equals 2, and somewhere over here also. Bright spot corresponding to m equals 2. Okay, so what angles are given? Angles are given. So let's say you measured these two angles. Angle to the second order fringe of the red light. Second order of the red light here. Second order fringe, it's this one. Of the red light. So that angle is measured. So let me use also red maybe. So this, right? And that angle is, what's the number? 53.2 degrees. So let me write, so theta 2, which way, theta 2 with upper script r. Subscript 2, upper script r. Okay, it makes sense. 2 because it corresponds to m equals 2, upper script r because it corresponds to the red light. And that angle, let me write it somewhere on the side, All right, theta 2 upper script r equals to 53.2 degrees. 53.2 degrees. Then angle about the blue light, one of the blue fringes are given. Which one? I think it's the corresponding to m equals 1. There, yeah, the first order fringe. So this angle is also measured to the blue m equals 1. Okay, so that is angle theta 1 upper script x. So it's basically your experimental setup, and you measured these angles. So you know, and you want to calculate the wavelength of an unknown light. Let's say you don't have a spectrometer, so you use this. So now let me write theta 1 x equals to 20.6. 20.6 degrees. So we need to find lambda x. Lambda x. We need to find, as I wrote, lambda x. Yeah, it's a long, sounds like a long statement, but the solution is reasonably simple. If it's a problem about diffraction grating, there is nothing else but these two statements. The first statement allows you, d sine theta equals m lambda, allows you to find these angles, which are given. But as I said, as I told you in the lecture, right, several times, measuring angles in the lab is not very convenient, right? For me, I wouldn't like it, right? So it's easier to measure distances, right? So for example, this, let's say this will be y1, right? Or that will be y2. So measuring these distances are more easier, right? So that's why the second equation is given. Ym, those distances, equals L times tangent of those angles. So first equation give us directions, angles to the bright spots. This distance along the screen to the bright spots. In this case, angles are given, so we don't need actually the second equation. Since we don't need to measure angles, they're already given, so we just need to use only the first equation. So equation d sine of theta m equals to lambda, m lambda. Let me write the way I wrote there, m lambda. Okay, I can frame it so it's sort of, it's in general. And now we need to apply this equation twice. For the red light for the second order fringe, and for this unknown light for the first order fringe, because that's what is given. So first order and second order, m equals 2, m equals 1. So d, and d is exactly the same because the same grating is used. So distance between slits exactly the same for both lights, right? So d sine of theta 2 upper script r equals to 2 lambda r. So for the red light, for that fringe, second order fringe, and now for the first order fringe of this blue light, this unknown light, again, the same d sine of theta 1 upper script x, m equals 1, so this is just lambda x. So two equations, and now let's see what can be done. How many unknowns? D is unknown, not given. Then this angle and this angle are given, this is given, lambda x is not known. So we have d and lambda x, two unknowns. Two equations, two unknowns, it's a solvable system. How you can solve it, it's up to you. You can, for example, take a ratio of this equation versus that equation in order to dump d. But let me do this way. I can solve for d the first equation and then shove it into the second equation, the value of that d. And the problem will be solved. Right. So now let me solve the first equation for d, because d is unknown, right? So d and this wavelength. All right, so it will be 2 lambda r divided by sine of theta 2 upper script r. Okay, I'm not going to calculate. I will just plug the whole thing as it is into the second equation. And right, and here it's already our unknown, lambda x. So I'll just rewrite this with that. So lambda x equals this 2 lambda sub r divided by sine of theta 2 upper script r times this sine of theta 1 of an unknown light. So all these are given in the problem. You can calculate, plug them. I'm not going to do that. I will just write down immediately the answer. Right. So it will be 553.7 nanometers. I'll just use my notes in order to save time. So you see, problems about double slit and diffraction grating, again, we spent quite some time deriving these conditions, right? But in terms of application, it's quite simple, especially for double slit. It's just this equation and nothing else. You can sometimes see two laser lights simultaneously illuminate the double slit, like over here we had for diffraction grating. Again, you'll have two sets of interference fringes, and something is given, but again, you just need to apply this equation, for example, twice, and solve for what needs to be found, right? Okay, so I'm not going to discuss double slit, right? But it will be in my notes. It will be in my notes. Okay, so now, all right, I'm thinking about this problem. Should I discuss it? Ray optics. You know what? Let me drag this through this. And as I said in the lectures and the recitation classes, problems about ray optics kind of demanding in terms of geometry. And that's where students most of the time struggle, because application of the Snell's law and law of reflection, it's quite reasonably simple. But seeing how to find that angle or this angle, play with triangles, find the right triangles in order to find some angles, right? So that's where these problems are demanding in geometry, right? So you need to remember geometry quite well from your high school years. Right? Okay, so let me scare you with one of the problems. It's not actually that bad, but again, only in terms of geometry can be a little bit scary. And after that, we will discuss two problems about lenses. But lenses are usually simple, reasonably simple, right? Except for, as I told you, ray tracing. That's where students struggle. Right. Okay. So let's see if I can start erasing. So that will be 11, problem number 11. So we have a prism made of glass. And sort of, if you look at top view, it's sort of like an equilateral triangle. So two sides are equal to each other, right? Or two angles equal, right? Okay, so let me draw the picture. I need a big one. You know what, let me use a ruler. So this will be base. Because I worry about geometry, so that's why I decided to use this ruler. So that's the base. Then, okay, erase slightly. So let's say this is the center, right? So that will be this side, which is equal to this side. Basically, it's, as I said, equilateral triangle. Oh, no, not equilateral. Equilateral, three sides are the same, right? So only two sides the same. Sorry, two sides are equal. Right. Let me label these points. Right. A, B, and C. So these points, right? And these angles are equal. So let me give you, so this angle theta and that angle theta, they're equal. Then index of refraction of the glass is given, right? So this is glass. Should I? Yeah. So that is glass, and N2, right? Yeah, N2 equals to 1.5. Index of refraction. It's a ratio of speed of light in the vacuum over speed of light in the medium, in this case in the glass. So of course here it's air. Outside here, outside it's a N1 equals to 1. It's air and glass. Then, okay, so now we take a laser light, laser pointer, and shine it parallel to this base, to this line. Basically, we shine it this way, right? Okay, let me draw this. Parallel to the base. Okay, let me go slightly higher. Yeah. So it looks like parallel. So that's our incident ray. This line is parallel to that line. Right. So then, of course, this ray will be refracted and gets inside of this prism. Let me draw that. And in order to draw that refracted ray, let me draw also a normal line. Normal line, of course, it's perpendicular to that surface. Let me draw this dash line. Right, so normal line, because you remember angles defining direction of these rays measured from the normal. So that's why I needed to draw that line. Right, and so now a refracted ray inside of this prism. Of course, since since ray propagates from the medium which is less dense to the medium which is more dense, of course, angle of refraction is going to be smaller, right? So let me draw that angle of this refracted ray. So it will be this, right? So that is angle of incidence, which we label it theta 1, angle of incidence. Then this angle of refraction, theta 2. And then what happens now? A ray is at that interface, at the boundary between glass and air. Of course, there will be another refraction. So first a refraction at this point, and now will be another refraction. And in order to draw a ray in air again, I need to draw a normal line, and then I will be able to draw a new refracted ray. So again, let me draw the normal line. So that normal line is going to be something like this. And so now, since it propagates from the medium which is denser to the medium which is less dense, of course, angle of refraction now is going to increase. So this angle, it's, let me label it theta 3. So now it's angle of incidence, and angle of refraction is going to be larger than theta 3. So it means that it will propagate somewhat like this. So that's the final refracted ray, and we need to find this angle, theta 4. That's our unknown. So two refraction at this point, that point, and we need to find that angle of refraction. Yeah, it's like, yeah. So let's start analyzing. So this line is parallel to that. And, yeah, another angle is given, this angle. I'm looking, something is still missing. Okay, so this angle is 50 degrees. 50 degrees. Right. Okay, now I can now I can start, because before it was kind of something else. Look, since this side equals to that side and this angle equals to that angle, so we can find this angle's theta. Let me erase now this, because the sine of all triangles sine of sum of all angles in a triangle must be equal to 180 degrees. So 50 plus theta must be equal to 180 degrees pi, right? So let me write that down. So first, look at the triangle A, B, C. So theta plus 50 degrees equals to 180 degrees. As a result, theta equals 180 minus 50, 130 divided by 2. So it will be 65 degrees. 65 degrees. So theta, 65 degrees. So that is 65 degrees. We just calculated. Now next, look, if this is 65 degrees, then what can you say about this angle? You see, this angle and that angle, they're the same, because this line is parallel to that line. So two parallel lines, if you intersect with a straight line, that's what this side does, right? So this angle and that angle the same. You remember geometry. Two parallel lines and intersect them with another line, these angles are equal. So that is will be also theta equals to 65 degrees, this angle. And as a result, now we can get the angle of incidence, theta 1. Look, this is a normal line. So the whole angle is 90 degrees. So if this is 65 degrees, so then that angle, which complements this one to 90 degrees, must be equal to 25. So angle of incidence must be equal to 25 degrees. Right? So did I get it right? Yeah, 25 degrees. Right. So then these two. So then theta 1 plus theta must be equal. So these two angles equals to 90 degrees. So as a result, theta 1, which is angle of incidence, it's 90 degrees minus 65 degrees equals to 25 degrees, right? You see, lots of geometry, and that's what I told you. That's the major issue with the problems in ray optics. You have to be very, very comfortable, smooth with geometry. Right, so now we know the angle of incidence, and so now we can apply Snell's law in order to find angle theta 2, angle of refraction. So basically it's this angle. So now we found angle of incidence. Let me emphasize that this is angle of incidence. Angle of incidence. In terms of physics, it's a trivial problem. Snell's law over here at this point, Snell's law over there, and that's it. But geometry makes it complicated, reasonably complicated. All right, so angle of incidence we found, and now Snell's law at this point, which I label it, okay, let me label it as point D, this point D. So Snell's law at point D. So it means that N1 times sine of theta 1, which we just found, equals to N2, index of refraction of glass, times of sine of this angle theta 2, angle of refraction, sine of theta 2. So this is given, this is given, this is given. We can find angle of refraction. So let me emphasize, so pretty much now we can find this. So we're just slowly moving from this to that, and then to this angle, and then we will have to find that angle again using second time Snell's law. So theta 2 equals to, pretty much this goes to that, and then take arc sine. So it will be inverse sine out of N1 over N2 times sine of theta 1. So all numbers are given. Again, N1 is 1, N2 1.5, theta 1, we just found 25 degrees. So you can calculate. I will look at my notes. 16 degrees. So that's angle. So now we are inside of the prism. So now we just need to create some mass in order to find angle of incidence theta 3. Now our next sort of local goal, we need to find this angle theta 3, which is angle of incidence for the refraction at this point, at that point. So now our local goal theta 3. So how can we find that goal, that angle? Look, I'm thinking this way. What can you say about this angle? You see, it's a 90 degrees. Because this is a normal line. You see dash line, it's a normal line. Normal to this line, to this side. So that is 90 degrees. And that angle 90 degrees consists of what? This angle of refraction, which we just found, theta 2. And that angle, let me label it somehow, this angle. Which way I label it? Oh, I didn't label it. So that angle of, let me call it beta. Beta. So beta plus theta 2, they complement each other to 90 degrees. So now, second step, beta plus theta 2 equals to 90 degrees. Okay, so theta 2 we found. So from here, as a result, beta equals to 90 degrees minus 16 degrees. So it will be, 64. Yeah, 64, right? Oh no, 74. 16, 74. Yeah, 74. Sorry, 74. 74 degrees. So that is 74 degrees. Okay, and now look, guys. Look at this triangle. So this is point D. Let me label this point as, which one? A. I mean E. This point, let me label it as E. Look at this triangle. D, A, E. Triangle D, A, E. Sum of all angles, this plus this plus this, must give us 180 degrees. We know that angle, we know that angle. We should be able to find this angle easily, right? So now let me write it down. So 74 degrees plus 50 degrees plus angle of AED, angle of AED must be equal to 180 degrees. So we can find this angle. So angle of AED will be equal to, okay, let's calculate. So this will give us 130 minus 74, 130 minus 74. Okay, I'll look at my notes. 56 degrees. 56 degrees. So that is 56 degrees. So it's at this angle, 56 degrees, which we just found. Again, in physics, we just apply Snell's law, nothing else, but we have to walk around looking through all the triangles in order to find this angle, that angle. That's ray optics. Right, so, and now we're getting closer. Look, this angle 56, then this angle 56 plus this angle theta 3, if you add them, you're getting 90 degrees, because again, this is the normal line, normal to this side, right? So this plus this 90 degrees. So of course, this angle, it's a 90 minus 56. We're finding angle of incidence for the second boundary, for the second interface. So we're getting very, very close to the end. So now, all right, 56 degrees plus theta 3 equals to 90 degrees, right? Because again, that line is perpendicular. So from here, we're getting, so theta 3 equals 90 minus 56. So it will be 34 degrees. 34. So that's the angle of incidence. 34 degrees. So that's the angle of incidence. Angle of incidence for the second interface. for this boundary. So that's the angle of incidence. So, okay, now we have angle of incidence and we should be able to get angle of refraction using Snell's law. Second point where we're going to use actually physics Snell's law. Otherwise, we just need to, between those 2 points where you apply Snell's law, we have to walk around applying geometry, right? Nothing else. So, right, so now Snell's law at point E. Right, so now Snell's law at point E. Again, but now n2 times sine of theta 3. So because index of refraction of the glass, it's n2 times sine of angle of incidence, it's a sine of theta 3. And on this side, again, it's air, n1, because around this prism there is an air. So n1 times sine of theta 4. And that's our unknown. And actually, that's our final unknown. Okay, so now let's solve it again, like here. N1 goes to that side, and then you have to take arc sine, inverse sine, in order to get theta 4. So theta 4 equals to inverse sine, and inside it will be n2 over n1, n times sine of theta 3. Sine of theta 3, 34 degrees. Okay, so now I will again look at my notes one more time, and the answer is 57 degrees. It's already mentioned that several times. In terms of physics, just application of Snell's law twice, that's it. And the rest, you just need to look carefully at the geometry. So enough. Pretty much we discuss physics and of course refreshing geometry. It's impossible to refresh everything, right? We will have to spend like the whole semester probably again refreshing geometry. So the last piece, let's discuss lenses quickly. Oh, usually application of lenses much easier. Okay, and then we'll call it a day. Right. Probably at this point you're scared by these ray optics problems. But I will try to find where geometry important but not as complicated as, for example, here. Because I have to be reasonable, at least try to be reasonable. Okay, so now will be number 12. Okay, I guess I can start erasing. Number 12. Okay, I will leave the last application of Snell's law. Okay, so one converging lens and then diverging lens. Yeah, we're getting closer to 4 hours, right? So it's a 4:50 and 8:15. So yeah, as I was planning. Converging lens. Yeah, first of all, it's 12, number 12. So, converging lens, right? And then diverging. Although it's not, it's very fresh because we just discussed it yesterday and the day before yesterday, right? Just recently, but why not? We can practice more. So, focal length. In front of 30 centimeters focal length. Okay, so focal length is 30 centimeters, and since it's a converging lens, of course we need to remember sign of sign convention, right? On the formula sheet, of course, I'm not going to write sign convention. What I'm going to write, of course, this a lens formula and formula for the magnification. But sign convention, basically, we just need to remember. So if image distance negative, it means image is virtual. If S prime is positive, image is real. And then magnification, if it's positive, it means image is upright. If it's negative, image is inverted, right? So those that sign convention is quite logical, right? And if you solve a few problems, you should remember that. And of course, the focal length. For a converging lens, focal length is positive. For diverging lens, focal length is negative. In order to write that formula, in order to use that formula properly. So converging lens, so it means that F is positive. So plus 30 centimeters. Okay, I should have used probably blue till the very end. Then object. Size of the object is 1 centimeter, and the distance to the object is 10 centimeters. Yeah. So that's what is given. So we just need to find image and analyze it. Is it real or virtual? Is it upright or upright or inverted? I combine upright and inverted and call it upverted. Okay, after 4 hours of yapping, it happens. So first, ray tracing and then algebra. And again, usually students do reasonably well with algebra, but ray tracing, lots of problems. So part A, ray tracing. And yeah, I need to use my ruler. So usually I start with optical axis, because everything is around that axis. Right. And so the lens, let me draw it here. Converging lens. And 3 special points. Our object distance S is less than focal length. It means that the object is within the focal distance. So let me position focal point over here, somewhere reasonably far away, right? All right, so let me position it here. So that's the focal point, near focal point, and then somewhere over here there will be second focal point, right? F. Right. And this is the center of the lens. 3 special points. And so object is 10 centimeters, so it's a 1/3. So the object is somewhere up here. So that's our object, right? Roughly. Okay, so that's it. And now we can start applying ray tracing. 3, you need to remember 3 typical situations, 3 rays. Although 2 is enough, right? But I'm going to use them all. So the first ray, of course, this tip sends rays in all possible directions. Pretty much. All right, there, so pretty much in all directions. So we need to find, of course, we can find out of that infinite number of rays the one which goes parallel to the optical axis, because we know how the lens, converging lens, treats that ray. It sends it through the far focal point. So if you pick this ray which is parallel to the optical axis, right? So ray number 1, then after the lens, that ray will be sent through the far focal point. So that's ray number 1. Right? You just need to practice a few times, and that's not complicated, not that complicated. Now, the second ray, yeah, that's where some people and some students sort of confused, because this, according to the situation number 2, that typical situation number 2, if a ray goes through the near focal point, then lens sends it parallel to the optical axis. But in this case, if we send a ray from the object through the near focal point, it just goes who knows where. Just it's not going to be involved in our image formation. So we need to do this. Connect the tip of the object with this focal point with the dashed line, and pick this ray which propagates towards the optical axis along this line. That will be our basically ray number 2, because lens doesn't care if a ray was generated, for example, at this point, or this point, or this point, or over here point, if I extend, for example, right? What lens cares is about a direction. If a ray comes along this direction, that lens grabs it and sends it parallel to the optical axis after that. Right? So that's how you need to find a ray number 2. Right? So pretty much draw this straight line and pick the ray which goes along that line towards the ray, towards the lens. And so after this, the lens will send it parallel to the optical axis. So that's our ray number 2. That's probably one of the most, I cannot say complicated situation, but you need to pay attention, right? And so these are 2 rays, and of course the last one, the trivial one, goes through the center of the lens. So that's ray number 3. So you see on this side of the lens, yeah, and of course I wanted to mention this. Each of these rays uses one of these special points. Ray number 1 uses far focal point. And after this, not a single ray is out of this supposed to use that point. Then ray number 2 sort of virtually uses focal point, near focal point, right? Virtually, because just travels along this line. And ray number 3 just goes through the center. 3 special points, 3 rays. Okay, so now rays are diverging. So where is the image? In order to see the image, you need to look through the lens. It means that you need to position your eye over here. You need to position your eye over there in order to see that image. Otherwise, you wouldn't be able to see. That image is going to be virtual. So how can we find that image? So now your brain start creating this image, start analyzing. So what does your brain think? So it sees that this ray travels along this direction. So it analyzes and thinks that the source of this ray lies somewhere on this line. Right. Along this line somewhere. Right? Then it sees this ray number 2. And of course analyzes in the same way. So since ray travels along that direction, it means that the source of this ray lies somewhere on this line. I slightly went down. Right. And the same ray number 3. We just need to extend it because that's the thinking of your brain. And as a result, you see all these rays intersect at that point. So your brain is going to see an image at that point. So let me draw it. So that's image. And it's just a pure your brain production. So it's only your brain is going to see that image, of course. If you position over here the screen, you're not going to see anything on that screen. Because actually, effectively, there are no rays traveling to that screen. It's all in your brain. It's a pure brain production, right? So that's where image. So since it's not real, right? So it's only in your brain, right? It's a virtual image, right? So again, you remember I told you that this sort of tests that you can use in order to convince yourself that this image is virtual. Imagine positioning here the screen, and of course on that screen you're not going to see anything. It means the image is virtual. Or since this image is created by diverging rays, you see rays are diverging. and your brain collects them, right? So since the image is created by diverging rays, the image is virtual. So we can write that image is virtual. And so the second part of the characterization of this image, since image and object are in the same directions, so upright, this image is upright. So it's an image virtual and upright. So we finished characterizing this image. And we found its position approximately where that is, and we characterize it. So that is a ray tracing part A. Now part B, let's actually calculate exactly where the image is going to be, what's the size of the image, right? And using sign convention, we can characterize actually the image about being virtual and being upright. So now let's do the second part, algebra. Again, I'm not writing its calculus, no, it's just the algebra. So the first you need to apply, of course, the formula for length formula. So 1 over f equals to 1 over s plus 1 over s prime. Of course, you can solve it for s prime. So it will be 1 over s prime, it will be 1 over f minus 1 over s. And you can bring it to the common denominator, flip it, and you will get that, okay, I will write underneath, s prime equals to s minus f. It will be in the denominator, yeah, s minus f, and numerator s times f. Okay, so now we can plug numbers. S is 10. In this case, there is no point of converting into meters, although you can if you want. Just the answer will be in centimeters if I'm not going to convert. Then f, 30 centimeters, and divided by 10 minus 30 centimeters, right? So of course, you see, the number is going to be negative. I will just look at my notes for the number. Okay, minus 15. Minus 15 centimeters. Okay, so what does it mean? It means that the image is positioned at 15 centimeters and the image is virtual. You remember sign convention. If s prime image distance is negative, it means that the image is virtual. Right, so it means that, all right, virtual image. Right, and at the distance of 15 centimeters. So that's the first part. Now the second part, of course, we need to use magnification in order to get information, about magnification and information about image being upright or inverted. So now the second part, m equals minus s prime over s. So minus and minus 15, because that's the value of s prime which we just found, and divided by s, 10 centimeters. So minus and minus plus, and magnification is 1.5. Right. Plus. Okay, I should have written, emphasized on plus. So that plus means that the image is upright. If you had minus over here, then of course it would mean that image would be inverted. So this is upright image. And so sometimes also the problem can ask about the size of an image. So that is h size of an object, h prime size of an image. So we can use again magnification, but now we just need to look at the absolute value. Now we interpreted plus or minus in order to get second piece of information, but now we just need to find the magnification actually. Now we don't need those pluses or minuses. So h prime over h. Again, we derived that in the lecture. So from here, h prime will be absolute value of magnification times the size of the object, as it should be. Because magnification is just a ratio of the image size versus object size. So 1.5 times 1 centimeter, so it will be 1.5 centimeters. Again, as I said a couple of times, here in this part, most of students do reasonably well, but ray tracing, you need to do it by yourself at home, right? So just close the book on notes, just draw the picture and start drawing. If you get stuck somewhere, okay, spend a little bit of time thinking, then open the notes and see how it's done. And again, continue by yourself. But you need to do it by yourself. You need to realize where you can get stuck. Because if you think that I saw something, I will be able to draw it on the exam, no, it doesn't work. You will realize very, very soon that something is missing in your understanding and you don't know how it should be done. Okay, so now the last problem, but I'm going to just draw. I'm just going to draw ray tracing. And calculations you can just look by yourself. So diverging lens. Let me look at the diverging lens, ray tracing, and we'll call it today. So now diverging rays. Lens. Diverging lens. Okay, focal length 30 centimeters. It sounds like, no, numbers are different. Focal length 30 centimeters, immediately write down that minus, right? We need to insert information about the lens into that equation, and that information goes into that equation through the value of f. Lens is diverging, it means focal length is negative. So minus 30 centimeters. Minus 30 centimeters. And object is positioned at 60 centimeters from the lens. So it means that object distance s is 60 centimeters. So it's outside of the focal length. Outside of the focal length. Right? And the size of the object, h, is again 1 centimeter. Yeah, it's 1 centimeter tall. Okay. Now I can erase this as well. And optical axis. Again, I need to estimate the amount of space I might need. Okay, so let me go slightly lower. Since I'm going to do only ray tracing. So optical axis, and now diverging lens. All right, let me draw it here. Okay, if I need, I can make it bigger at some point. So object is, okay, I use blue. I know, first I need to draw those 3 special points. All right, so the center and 2 focal points. So focal point is 30, and then the object will be at the distance 60. So let me draw it like this. So this will be focal point near, and this will be my far focal point, right? And the object, 60 centimeters, it's a double of that. So this. So that will be approximately, that's where our object is going to be approximately. Let's see. Okay, it should be good. Object. Okay, it looks like everything that we need to start ray tracing is here, and so let's do it. We just need to find an image of that tip. Again, that tip sends rays in all possible directions, right? So we just need to use only 3 of them. Actually, again, 2 is enough, but I'm going to use all of those special rays. So the first ray, when we discussed that yesterday, in the lecture yesterday, right? So if a ray ray number one. If a ray travels parallel to the optical axis, then the lens, now it's a diverging lens. Of course, the lens will diverge it away from the optical axis. Right, so let me first draw it. Ray parallel to the optical axis. Right. So it's ray number one. And then this lens diverged somewhat in that direction. And it will diverge it in such a direction. If you extend that direction, if you extend that line this way, it should go that line through the near focal point. So pretty much what you should do, just use the dashed line and connect the point on the lens with the with this near focal point, dashed line, because that's where there is no ray. We just need to find a direction along which ray actually propagates. So along this direction, ray is going to travel. So that's ray number one. Sort of this point near focal point is kind of virtually involved, right? So extension of that array, if you extend it in this direction, it should cross, it should pass the near focal point. Converging lens would diverge, okay, would send the ray through the far focal point. That's converging lens. Lens converges rays, but this is diverging lens. It diverges it away from the optical axis and in such a direction. So if you extend it, that direction should go through the near focal point. So that's how you should draw ray number one. Now ray number two. Basically, it's a reverse situation. You remember how first case, first ray, and second ray, second case are connected. Reverse the direction. So here, if you reverse the direction of the first ray, so what you have, if you aim the ray towards the optical, towards the focal point, if you aim towards the focal point, then after the lens, that ray should go parallel to the optical axis. So, but now, of course, that must be done from our object. So, aim towards the focal point. It's like here, if you aim towards the focal point, so now we have to aim towards that focal point. Oh, I don't have enough. My ruler is not long enough. Okay, I hope it should be enough. All right. So, up to the lens. Of course, we have solid line, right? And then it should be dashed line because over here there is no ray. Now that ray will be sent parallel to the optical axis. So we're just aiming it. But of course, after this point, this ray will travel parallel to the optical axis. So ray number two. Reversing, aim to the focal point and then parallel. So we aim to the focal point and then it's parallel to the optical axis. So pretty much at this point, it's enough in order to get the image, right? But we still have ray number three, so let me draw it as well. Right. So it should be good. This, yeah. Right, so ray number three. And again, you see, these rays are diverging after the lens. So in order to see that image, again, you need to position your eye over here. Otherwise, you will never be able to see that image, right? So you need to position your eye over there. And again, your brain will start drawing that image in your brain. Right. So again, it will start analyzing in the same way. So since this ray travels this way, so it means that the source is somewhere along this line. Then this ray travels that way, so it means that the source must be somewhere along this line. And the ray number three, it's already, we don't have to draw anything. So you see all these three rays intersect at this point. Okay, extensions of these rays, intersect at that point. So that's where the image is going to be. Again, in your brain, nowhere else. Again, the test, you remember, if you position a screen over here, you're not going to see any light, right? Because again, that's your brain extending these directions in order to see the image. So that image exists only in your head, in our head, of course, right? So that image is virtual, of course. Virtual. And now upright or inverted, obviously, since object is up and image is up, so it's upverted. Why again? Why are you using upright? Upright. So up, right. So that's how you should analyze diverging lens. Okay, I'm not going to do calculations. Again, it is in my notes. I will scan them and send my notes to you anyway, so you can look by yourself if you want. To practice. No, I will sit here. So that's it. That's what I was planning. So 8:43. So it's 4 hours 10 minutes, right? Again, the record was 4 hours 30 minutes, right? Yeah, because the amount of material is much larger than for the first midterm exam or for the second midterm exam. Because when we move into optics, usually we move a little bit faster, right? Okay, so I will sit here waiting. So if you do have questions, you can start asking. If not, then you can go, right? And once you all go, then I will stop this stream and start scanning my notes and start making the video.